Okay, Chris, I think we should
We
start. Huh?
should start and keep on time. So welcome everyone. I know it's an ungodly hour in most of the places on the planet, but we start at 6:30 a.m. Central European time. We have a session that is dedicated to double compact objects and, you know, any ejecta or any accompanying electromagnetic or particle emission from double compact objects. We'll start with talks on a stable mass transfer and wind effects on double compact object formation. We'll go to double neutron star mergers and the mechanics of those mergers. Then we'll go to double neutron star actually formation sites. And then we'll continue to talk about formation mechanism, and actually we'll finish up with a kind of exotic subjects for most of the astronomers, which is primordial black holes. Okay, and when we'll have some time for discussion. We'll keep talks to 20 minutes, and we'll keep 5 minutes for discussion, and each speaker will get a 3-minute warning from me. And when you want to have a question, raise your hand, and when there is a question time, you can just turn on your mic and turn on your camera and start speaking as well, either or. We'll be also watching chat. If you want to put a question on the chat during a talk, we'll repeat that to the speaker. Okay, so let's start with the first talk, and we give the floor to Andras. Andras, please share your screen.
Yes. Can you hear me?
Yes, we can hear you, and we'll turn off our mics. And
okay, so I start. So yes, I'm going to talk about formation of gravitational sources. So it's not directly related to explosive events, but I still hope that you will find it interesting. I won't have time to cover the stellar wind parts, so if you're interested, please let me know. So in this line of research we are in, we are actually interested in gravitational waves because we want to learn about the evolution of massive stars. It's a very indirect way to learn about these objects, but keep in mind that they're very rare, as suggested by the initial mass function. They're also very short-lived, but they are very important for a bunch of essential astrophysical processes. If you want to understand them, we also need to understand their binary interactions, because 70% of them are thought to be interacting, as suggested by observations. Some of them will end up as merging binary black holes. So we can actually use the LIGO population properties to infer something about these uncertain processes that they go through during their lives, if we know more or less how they form. There are many suggested formation pathways. So at the end of the day, you need black holes that are close enough so they can merge within the Hubble time due to gravitational waves. So they can form, you can form the black hole separately, and then they can be brought together by in a dense environment, for example, in a globular cluster, or they can also form from an isolated massive binary. In the latter case, the key point that you need to remember is that they cannot have more than a few tens of solar radius separation if you want them to merge within a Hubble time, as suggested by this plot. And if you just naively put two massive stars at such a short separation, you will find that eventually they will merge before they would form black hole binaries. So they need to start out from a larger separation. So there needs to be a process that eventually shrinks the systems to a short orbit. Two of these commonly suggested processes are, one of them is a common envelope, which occurs after an unstable mass transfer, and a second would be a stable mass transfer. This can occur if we assume that the black hole accretion is limited by the Eddington limit, and we have high mass ratios. So in the isolated binary formation channel, I already suggested, I did not suggest, but typically common envelope is that's found the most uncertain step in this process, but there are many others. Here I listed some of them. I can't cover them, but I highlighted the ones that I studied in my project. So these ones are the first, stable mass transfer, the mass transfer stability criteria, and the uncertainty at what stage the convective envelope develops. So we would expect that these uncertainties have an effect on the observable properties of the merging binary black holes that we can measure from LIGO. So they would change the merger rate, the mass and mass ratio distributions. But perhaps more importantly, they also can change the dominant subchannel. So in some cases, we would find that the stable channel is the most dominant one. In other cases, it turns out the common envelope channel is the more dominant one. So just a little about the methodology. I use a rapid population synthesis code called SIBA. Basically, we perform the Monte Carlo simulation. So we sample binaries following some distributions. And then from this code, we got the evolution of massive binaries. And from this evolution of massive binaries, we can actually obtain the population of gravitational wave sources. For rapid population synthesis codes, unfortunately, we have to use simplified physics, but currently this is the only way that we can simulate this high number of sources. So in order to study these processes that I already mentioned, but these are characterized by those parameters that I'm showing you on the right. If you don't know what they mean, don't worry, I'm trying to explain later. But the point here is that we try to vary these parameters within a reasonable interval to understand their effects with the merging binary black hole population. For the reference, I added a table about the assumptions and the alternative values for these parameters. I would like to stress that sometimes we use constant values, and we don't say that this is realistic. We like to understand their importance on the population. So we created models. We ended up with 16 model variations, and we simulated each of these model variations on metallicity grid outlined below. So it would be very boring to go through all these 16 models. So I would just like to highlight the most important results that we find. So let's start with the uncertainties in the first table, mass transfer. So the point here, sorry for the ugly drawing, but I hope you get the picture. Eventually, the primary fields in row slope, there will be mass transfer. There will be probably an accretion in this form. And in this case, we can accept that the accretor would spin up very fast to critical rotation. And in this case, it's not easy to imagine. It's easy to imagine that the mass transfer would not be conservative. So some matter would leave the binary. Also, it's possible that the donor would swell up and there would be additional matter leaving through the LG point. So there are two major uncertainties in this picture. First is the amount of matter that is accreted. We characterize this by beta, which I'm going to refer to as a mass accretion efficiency, and the angular momentum that is actually lost from the system. This is characterized by gamma, which is the specific angular momentum lost from the system over the specific angular momentum of the binary. So these two parameters will obviously determine what's going to be the period of the system after the first mass transfer. And I'm going to show that this is actually very important for the merger rate of the stable channel. For this, I'm going to consider a bunch of systems before the second mass transfer. So we're going to have an evolve star black hole binary. I'm going to fix the black hole mass, and I'm going to consider a number of systems for a range of donor masses. And I'm going to plot them in a mass ratio orbital separation space. So the y-axis shows the separation in log space, the x-axis is the mass ratio. And then we have two different models for different values of gamma. So first, I'm showing you the separation that these systems need to have by the time they form black hole binaries if we want them to merge due to gravitational within Hubble time. For this, obviously, we need to assume something about the black hole mass that the donor would form. And for this, we assumed that they would interact during the hydrogen shell burning phase. Is typical for the stable channel. So for example, at this metallicity, at the 60 solar mass, we find that 60 solar mass star would form a 21.8 solar mass black hole. So the second line that I draw is the orbital separation that this system need to have before the second mass transfer so that they would arrive at the black line. For this, I assume that what changes the orbit is the stable mass transfer. So as I already hinted, and it can be seen here, if the system actually have high mass ratio, a stable mass transfer can significantly shrink the orbit, given that we are below a critical mass ratio, above which we will assume that the mass transfer would be unstable. So I will explain this later. But for now, I plot the contours of our distribution from our simulations for the two gamma models. So these are the distributions before the second mass transfer. And we can see that for the gamma 2.5 model, there is a portion that actually merges through the stable channel, whereas for the other model, not. So we'd like to find out why it is. We know that these distributions are shaped primarily by the gamma and the beta, so the mass accretion efficiency, and the angular momentum loss from the system. And we find actually the gamma is more important. So to understand why that is, I also plot the initial separations that these binaries need to have so that after the first mass transfer, they would end up at the red line. So I would like to point out that when I construct these curves, I actually neglect the effect of the supernova on orbit, so that might seem a bit strange. And so it's only approximately good, but I would also like to point out that at this mesosphere, the supernova prescription that we used from prior actually predicts a pretty large fallback. So the kick the black hole would get is very small. And the last line that I'm going to show, I promise, is the initial separation that the primary needs to have if you want it to fill its enroche just when it evolved of the main sequence. So actually we see that if the required initial separation given by the green line is such that the first mass transfer would occur during a Mason phase, then gravitational wave source formation through the stable channel is not possible. And this is because if the donor is still in a May sequence, the outcome will be very different. In this case, the helium core is not formed yet. And as a result of the mass transfer, the helium core can actually decrease significantly and it will form lower mass black hole than it would happen with the mass transfer when the donor is already a giant. And we find that these systems, even if they survive the mass transfer, by the time of the second mass transfer, the mass ratio will be so high that it will be quite often unstable. So actually, we find the reason why for the gamma 2.5 model, the stable channel formation is not possible is because for a large parameter space, the required initial separation would be such that the first mass transfer would occur during a May sequence phase. And this is mostly because with such gamma, the orbit typically widens after the first mass transfer, and that's not the case for the gamma 2.5 model. Okay, so what is this effect on the astrophysical population? I show you here a stacked histogram. It shows the primary black hole mass for different channels. I also show the merger rate. So I need you to concentrate at this time on the green part, which shows the contribution from the stable channel. And as I already hinted, actually changing gamma 2.5 from 1 decreases significantly the merger rate from the stable channel. And this prediction is not sensitive to the assumed accretion efficiency. So moving on, I'm going to talk about the Masturbative criteria and how we assess it. So when we have a mass transfer, the Roche slope will change, obviously, because the separation and the mass ratio is changing. At the same time, the radius of the donor will also change as the star is trying to rearrange its structure. And we have to compare how fast these two properties change. In particular, if the Roche slope is receding back slower than the radius of the donor, then we have a runaway process. In that case, we have an unstable mass transfer, which can lead to common envelope process. So we introduced these two parameters, zeta L, which tells you how the Roche slope changes with mass transfer, and zeta ED, which tells you how the radius of the donor changes with mass transfer on dynamical timescale. If the zeta L is larger than zeta ED, then we say that it's going to be, the mass transfer is going to be dynamic unstable, and it will be followed by a common envelope process. So in SIBA, we assume constant zetas for each stellar evolutionary phase. And one of our model variations was actually to vary the value for zeta for giants with radiative envelopes. And I would also like to point out, because it's important, that stars with convective envelopes typically have a small negative zetas. So this means when they donate some mass, they will actually expand a little bit. So they are ideal progenitors for common envelope like mass transfers. Okay, so how did we, what did we assume for convective envelope? At what stage would the convective envelope develop? We followed two models from Ivanova and Tam, who assumed that this would occur at the constant effective temperature. And we also used the study from Clanky et al. 2020. He actually predicted that convective envelope would develop at a cooler effective temperature. Because of this, I will refer to the model from Clanky as the cool convective envelope prescription, and from Ivanova and Tam, I'm going to refer to the hot convective envelope prescription. So I'm going to, because of lack of time, jump straight to the plots of the astrophysical populations. So here I'm going to show this kind of plots a lot. These are 2D histograms. On the right, so each column refers to a different channel. The right one is the CE channel, the left one is a stable channel, and each row refers to a certain model variation. So in this case, We have the cool convective envelope prescription with low accretion efficiency, and the lower one is the same, but with high accretion efficiency. And the takeaway message here is if you use Klenke's prescription and with low accretion efficiency, the common envelope channel cannot produce high mass gravitational wave sources. This is because for higher mass, they cannot really develop convective envelopes. So the only way for the common envelope channel to produce sources is through donors with radiative envelopes, but then you will need to have high mass ratios at the onset of the second mass transfer, which you would think that is very difficult if the mass accretion efficiency is low. So if we increase the mass accretion efficiency, we see that we will have some high mass sources, but it's still low numbers. And it turns out that the mass ratio at the onset of the second mass transfer is further narrowed down by what we assumed about Abbe winds. We assumed that they're quite intense and they are metal independent. Okay, however, if we use the hot convective envelope prescription, then we will always have a significant component in the high mass regime from the common envelope channel, regardless whether we have low or high mass accretion efficiency. I would like to point out that in these model variations, in the high mass regime, still we find that the stable channel is the most dominant one. However, that's not the case if you use the hot convective envelope prescription with a gamma 1 model. In that case, the common envelope channel with the convective donor becomes the most dominant one. And we also find that they can produce a relatively wide mass ratio distribution. So you would wonder why that is. If you remember, if you assume gamma 1, most of the time the orbit widens of the first mass transfer, and actually that's beneficial for this kind of channel because you want the first mass transfer to be stable. You don't want the donor to have convective envelope. So if the orbit widens, it's more likely that at the second mass transfer, the donor would fill in the Roche loop at a later stage when it already develops a convective envelope.
Andres, okay, the last 3 minutes.
Okay, it's the last slide. So yeah, it's the effect of changing the mass transfer stability criteria. It always increases the merger rate of the stable channels. However, if we assume low accretion efficiency, it only affects the lower mass regime. This is something I couldn't explain why that is. If you're interested, just ask me. I can show you slides, backup slides. And it can also increase the mass. So yes, the beta in this case can also widen the mass ratio distribution. So these are my conclusions. If I can point out one thing is that the first mass transfer is actually turns out to be very important. So if you want to understand this channel, maybe we should look at Wolfram OB stars and infer the uncertain physics from there before we turn our attention to gravitational waves. Thank you very much.
Okay, thank you very much. It was a fast-paced talk at that time.
Sorry, I hope you could follow.
That's good. That's good. It's probably always good to mention that the person who proposed the channel, that stable mass transfer channel, was Ed van den Heuvel. So I was actually
it was mentioned
in my mind as a Ed van den Heuvel channel, but it's yeah.
Okay, no, but just to be on the safe side, his name was actually mentioned in the slide.
Sorry, I missed that. Sorry. Okay. Questions? Any comments on? Okay.
Okay, so I could have a question.
Please go. Go ahead.
Yeah, this is the similar exercise that we recently do for the Star Trek to implement some new strict condition for the common envelope. And I wonder if in your simulations, you show some figures, but how does the new criteria influence the distribution of the mass ratio? And do you also observe this peak around 0.5 due to this van den Heuvel channel, which demands the high mass ratio?
0.5 is what? Mass ratio?
The mass ratio, yeah.
Okay.
Of the black holes, the final mass ratio of the black holes.
Okay.
That's so merging the Hubble time.
Yeah, okay. Yeah, I'm vaguely familiar what you found in the paper. So we don't exactly find it. I always wonder why that is, but just generally, I see an important, so it also depends what you assume for mass accretion efficiency. And I find that the higher that is, the wider the mass ratio is if we increase this zeta. So if we allow more sources to go through stable mass transfer, along with that we have high mass accretion efficiency, then we see wider range of mass ratio distribution. But we personally did not see a peak around 0.5. It would be good to understand why we don't find that. Yes.
Yeah, I think it would be good to compare our results.
Yeah, but do you,
Interesting.
I don't know if you have time, but do you have any intuitive answer? Why would you observe a peak around 0.5?
This is because, as you said, for this Van den Heuvel channel, one needs to have the high mass ratio of the donor to the accretor during the second stable mass transfer. And in general, the final outcome for such systems that, they orbit shrink enough to merge in the Hubble time. They just end up with such a distribution that is strongly peaked around this 0.5.
Okay.
But maybe I need to check it more carefully.
But the comment to both of you, since we have two codes that work on the same channel and they seems to give systematically different answer, how would we know, observing gravitational wave population of sources, double black holes, double neutron stars, how would we know from which channel they came from, even if we already knew upfront that they came from binary evolution? Because I don't see a robust conclusion here. I don't see how would we know.
I agree. Maybe one thing that sorry. I was thinking maybe the time delay. So maybe if we have third generational gravitational detectors, you can see a signature in the merger distribution or redshifts, because I would find that the stable channel typically have higher time delays. So
good point. Good point.
Exactly. The time delays also, there was reported by some of the recent works that it is not possible to get high spin in this channel with this. It is harder to get the high spin of the secondary due to the tides. So maybe that would be some sort of indicator if we detect a high spin for the second black hole.
Oh, that's another good point. And we do in O3, we have one event that has an effective spin of 0.5 plus minus 0.2, but it's the highest spin in LIGO data so far. So that event would not come from a stable channel. It would have to come either from common envelope, because then stars are closer, or come from dynamical channel when you have a second generation merger.
Yeah, it seems so.
Are born with low spins. Yeah.
But may I ask you? May I ask a question? How did you get an observational time delay from these systems? How did you get that? Observationally speaking.
Yeah. So LIGO is doing that analysis, and from black hole merger distribution with redshift, they can assuming that the black holes are coming from stars. We know star production as a function of redshift. You can compare the two, and you can get delay time. So LIGO did publish a paper.
Okay.
So and it seems like delay time is consistent with what binary evolution predicts so far, at least in the common envelope channel. But I think the errors are so wide that I think it will accommodate at the moment both channels, both sub channels.
Chris, do I have time for a short question to Andres?
Yes, of course. Please go ahead.
So from the beginning of your talk, in the back of my mind, I was trying to picture the physical scenario where you would get gamma 1 versus gamma 2.5. Can you explain a little bit more what gamma 1 versus gamma 2.5 means? And how this is independent of mass ratio also.
Right. So yeah, obviously these are not very physical. They will obviously depend on the properties of the binary. So these are just constant values that have been sort of like inferred from observations or just some assumptions. By coincidence, actually, I find that the gamma 1 model is more, when you look at the population, is more similar when you would assume that the angular momentum loss from the system is that of the accretor. So this would probably happen if somehow the mass that is transferred would somehow be ejected very close to the star without the spinning up, I would assume. And I would say gamma 2.5, then that would mean that more angular momentum is lost. So there would be some additional physical process.
From L2 overflow, from material leaving from L2.
For example, yeah. But as I said, I don't think it's very realistic to model this by a constant value. It's just more like a sensitivity study. So
okay, so I should take your results as the low gamma, meaning roughly losing angular momentum from the accretor, and the higher that you have some additional angular momentum loss.
I would say yes, that would be a good way to think of it.
Thank you.
Yeah.
Okay, thank you very much for the talk. It was a good discussion. I think we want to switch to Bruno right now. And Bruno, please share your screen. And we'll have right now a talk about inner mechanics of neutron-neutron star mergers of magnetized neutron stars. Bruno, please, 20 minutes. We cannot hear you. Could you put on your mic?
Yeah, you should be hearing.
Yeah, okay, right? Good, very good, very good. Now we can see and hear you.
Perfect. Okay, let me just move it this way. Okay, so the title of the talk is From Whiskey to Spritz, which are the name of the codes that I used in the past and the code that I use now. So just to clarify this. And I work at University of Milano Bicocca. I'm also affiliated with the National Institute for Nuclear Physics and the National Institute for Astrophysics. And if you want to know more about me, I have a web page. So just a quick overview of what is the typical dynamics you expect from binary neutron star mergers. So that strongly depends on the total mass of the system, as well as on the equation of state of the neutron star, which is something that we don't know exactly yet. So I detracted here 4 different channels, 2 in red and 2 in blue. So the red channels are those that I call like the high mass scenario, and the blue channel the low mass scenario. So if the total mass of the binary is much larger than the maximum mass that can be supported by uniform rotation, then at the time of merger, you have essentially immediate collapse to black hole, and possibly you will not have not even at all. So all matter will just end up in the black hole. And so this is the most extreme cases, which is depicted with this line. If the total mass of the binary is just slightly above the maximum mass for a uniformly rotating neutron star, then you will go through an intermediate phase, which is with the formation of an hypermassive neutron star. This hypermassive neutron star will survive for less than 1 second and then finally collapse to a black hole surrounded by atolls. Essentially, the hypermassive neutron star is supported by the degree of differential rotation in the stellar layer of the star, but is losing angular momentum via gravitational waves, and therefore it collapses very quickly. In the low mass scenario, instead, the one depicted here in blue, you have that the total mass of the binary, it's below the maximum mass that can be supported by uniform rotation, but above the maximum mass for a TOV, so a non-rotating neutron star. In that case, by definition, you form an object which is called a supermassive neutron star. So in principle, this object could survive forever since it can be supported by uniform rotation. But since neutron stars are magnetized and we expect magnetic field to be strongly amplified during merger, because of magnetic braking, the spin will go down, and therefore also this object at a certain time will collapse to a black hole plus atolls. So if you imagine that this star will be strongly magnetized, something like a magnetar, then maybe it will collapse in less than 1 hour. And then you have the most extreme case in which the total mass of the binary is even below the maximum mass for a TOV, so a non-rotating neutron star. And in that case, you will just form a stable neutron star that will live forever. Okay, so this scenario is very extreme. We expect that most binary will probably go through these phases, an hypermassive neutron star or a supermassive neutron star system. But we have some cases in which probably we have the direct collapse to black hole. For example, GW190425 was a very massive binary, so that possibly went to this channel, so it produced a black hole immediately after merger. While in the case of GW17817, we expect probably that it went through an hypermassive neutron star phase. So I'm going just to talk about a couple of papers we did in the past with this whiskey MHD code that I wrote when I was a PhD student a century ago. And in this paper, we consider essentially simulation in 3D with the magnetic fields of these high mass binary resource systems. So binary resource systems produce or a prompt collapsed black hole or an hypermassive neutron star collapsed black hole. And we consider two different equations of state. A very simple ideal fluid equation of state. Consider both an equal mass system, which is the same system that is considered also in other paper. For example, for those of you that are familiar with the literature, the famous Misslink paper, as well as the paper by Ruiz et al. 2016 showing the formation of a jet. So this is quite a popular model. In this case, we investigated the evolution of the system with the field, magnetic field moment aligned with the total angular momentum, or maybe one field aligned and the other one anti-aligned, so up, down, or both magnetic field anti-aligned with the total angular momentum. And then we also consider an equal mass system in which two neutron star gravitational masses of 1.4 and 1.7. And then we also consider something a bit more realistic for the time, a piecewise polytropic equation of state named H4. In the case, we consider an equal mass system and an equal mass system. All models started with an initial magnetic field of 10 to the 12 Gauss. And this was the first paper, to the best of my knowledge, that considered an equal mass model with magnetic fields. So, and as I said, all simulations were performed with Whiskey MHD, which is an old code. Well, nowadays it's not, it's an old code based on the Einstein toolkit. So what I'm going to show here, it's a movie for one of the model, in particular the H4 equation of state, equal mass. So here you will see a rendering of the rest mass density, and on the bottom, the gravitational signal emitted by the system. So the star orbit around each other for approximately 5 orbits. So here we have the signal during the spiral. Then at a certain point they merge. During the merger, the production of strong shocks, so that you have a lower density matter that is expelled, as well the formation of hypermassive star that in very few milliseconds collapse to a black hole, surrounded by an accretion disk. On the slide, I will put the link to the YouTube version for this movie, for whoever wants to watch it later. What was important in this paper that we had a look at the evolution of the magnetic field. So what we have here is a series of panels showing the evolution of the magnetic field. So this is the initial configuration. For numerical reason, the magnetic field was confined inside the neutron star because we use what is called ideal magnetodynamics. So we assume infinite conductivity for the plasma, and that is a very good approximation inside the neutron star, but it's not a good approximation outside. So for numerical reason, we impose the magnetic field, we added the magnetic field only inside the neutron star. So here you see a cut of the neutron star. So yellow will be the surface of the neutron star, and then inside you can see the poloidal magnetic field. This is the time of merger when the hypermassive neutron star is formed. The magnetic field is quite chaotic. It has both a poloidal and a toroidal component. And then later you have the collapse to black hole and the formation of the torus. And this is the last panel, in which you have essentially the disk. This corresponds to a surface of around 10 to the 10 grams per cubic centimeter. And you have a low density funnel aligned with the spin axis of the black hole. This yellow surface corresponds approximately to 10 to the 8 grams per cubic centimeter. And then here you have the magnetic field lines, with the magnetic field being mainly toroidal inside the torus, and having an helicoidal structure along the spin axis of the black hole. So this kind of structure is very important because it can allow for the production of relativistic jets and can also have co-eventing jets. Unfortunately, by the end of the simulation, we were not able to see a relativistic jet actually being formed. But what was nice, and this kind of structure was common for all our models, both equal mass and unequal mass, and both with ideal fluid and H4. So this kind of structure seems to come very natural from numerical simulation of binary neutron star mergers. So as I told you, we didn't see any ejecta. In particular, on the left, I have a couple of panels showing on the top the Z component of the velocity. Blue means that you have infalling matter. Red means that you are outgoing matters. And in both, for example, the H4 equal mass scenario and H4 unequal mass scenario, essentially in the low density funnel, the matter is still falling into the black holes. We don't have any ejecta. In both panels, on the bottom, you have instead the relation between the magnetic pressure and the gas pressure. So white will mean essentially something that is magnetically dominated. In both cases, you see that the funnel is not magnetically dominated. And in order to activate the Blancos-Knight mechanism, which is supposed to be the mechanism that is going to launch a relativistic jet when you have a magnetic field, you really need a magnetically dominated region close to the black hole. So as I said, our simulation started with 10 to the 12 Gauss, and because of resolution, we were not able essentially to resolve the most small scale dynamics that can take place during merger and that can power the magnetic field growth. In particular, there have been simulation, for example, by QC collaborators, in which by using incredibly high resolution of the order of 10 meters, they were able to see that a merger, a magnetic field of 10 to the 12, 10 to the 13 Gauss can grow of several orders of magnitude. Unfortunately, the simulations were so expensive that QC et al. Just stopped the simulation soon after merger. So they were not able to follow what happens later. We know from the simulation of Ruiz et al. That if you start with a magnetic field that is much larger than 10 to the 12 Gauss, in particular in their case, they start with 10 to the 16 Gauss, at the end you can get a magnetically dominated funnel, and therefore you can get a relativistic jet. At the moment, as far as I know, the only simulation in which they were able to see the formation of relativistic jet in ideal MHD were the ones from Ruiz and collaborators, essentially. So what about instead the blue fast, the low mass scenario? So as I said, this one is very extreme, but this one forming a supermassive neutron star, maybe not. So a few years ago, I wrote a paper together with Tony Pidor and Rosalba Perna, in which we had a look at which kind of scenario you may have from binary neutron star merger. So we made the big assumption that the population of binary neutron stars were represented by the population we have in our galaxy. So of course, this is a big assumption. And then on the basis of the equation of state, we decided to see how many models were producing, for example, a black hole or via prompt collapse or via an hypermassive neutron star formation, which models instead will form a supermassive neutron star and which model will even form a stable neutron star. So here, for example, you have the distribution of initial masses, which is the Gaussian on the left. For all models, it's the same, of course. And then depending on the equation of state, we depict what is the final mass of the merger, and in particular with these dashed lines, we represent the region where, according to different equations of state, for example, you will have black hole formation, or either via prompt collapse or via the formation of hypermassive neutron star phase, or a very long-lived supermassive neutron star, or even more extreme neutron star. So you have different equations of state, for example, H4, APR4, which is still an equation of state is expected valid, according also to more recent observation of gravitational waves. And for example, in the case of APR4, again, if you assume that typical population of binary neutron star is the one of our galaxy, you get that a significant fraction, for example, merger should produce a long-lived supramassive neutron star. And then if you move to even more extreme equation of state, like MS1 or SHT, these one are actually ruled out nowadays because of observation of CW17 or 17. But in this, with this equation of state, you will even predict that most merger will produce a stable neutron star. As I told you, these are very extreme equation of state. They are very stiff and they are nowadays completely ruled out. But for example, APR4 equation of state is still consistent with the limit we get from gravitational wave signal. As you see, a significant fraction could produce a long-lived neutron star. Then there are also observations in X-rays that were done following short gamma ray burst. There is a famous paper from Antonia Rollinson and collaborators from 2013, in which by observing the X-ray afterglow following some short gamma ray burst, they see the formation of what are called plateaus. So essentially, for example, if we look at this plot, here you have a luminosity on the vertical axis and the time since the burst in a log scale. So for example, this is 1000 seconds after the burst. So the typical afterglow like curve that you expect is this dashed line going down. So the jet that is produced from the merger is just slowing down because of the interaction with the stellar medium of a jet. And therefore you just expect a power law. But observation in X-ray show that at a later time you have a sort of this extra luminosity with respect to what is supposed to be the one predicted from a decelerating jet. So it looks like there is new energy injected essentially in the jet. And the solid lines is a fit that Rollinson et al. Computed by assuming that the central engine, instead of being a neutron star plus a black hole, was a magnetite. So essentially a scenario in which you have a long-lived neutron star strongly magnetized. And this is something that, for example, we started to study a few years ago. This was a paper with the first author, Riccardo Cialfi. In this case, we consider that the evolution of also hollow mass binary transfer system. So we consider a six different binary transfer system with 2 different mass ratios and 3 equational states. And 2 of these equational states are going to produce a long-lived neutron star, while one at H4 is just there for comparison, is going to produce an hypermassive neutron star. So here, for example, I have the gravitational signal from these models. So all models have the same initial masses. What changes is just the equational state. In the case of the hypermassive neutron star, you have the spiral. In the case of the H4 equational state, you have the spiral, the formation of hypermassive neutron star, then collapse to a black hole. Changing the equational state, for example, if you go to IPR4 with the same total masses, you get instead a long-lived supramassive neutron star. So we follow the system during the spiral. We follow the system for around 40 milliseconds after merger, and then we just stop at the simulation. And if you go from a more extreme equational state, MS1, the one that was here, as I say, this one is nowadays ruled out. In this case, you have the spiral and the deformation even of a stable neutron star. And also in this case, we just stop at the simulation after a few milliseconds after merger. And on the bottom, you have the instantaneous frequency from the gravitational wave signal. And what is important to remember is that after merger, the gravitational wave signal is characterized by a characteristic frequency, and it is strongly correlated with the equational state. So what we did in this paper was to try to understand if the magnetic field can have an effect on this post-merger frequency. As I just told, the post-merger frequency is strongly correlated to the equational state, and so therefore it can be used to infer the equational state of neutron star matter. So here, for example, I have the spectrum from a few simulations, and I will ask you to focus on the green solid and the green dashed line. This refers to the same identical model with the IPR4 equational state, equal mass, one with a magnetic field pretty large, 10 to the 15 Gauss, and the dashed line without a magnetic field. And essentially, even by zooming in—
3 minutes.
Sorry?
3 minutes. You
Okay.
have 3 minutes left, okay?
Okay. So if you see at the position of the peak is not strongly affected by the magnetic field. So bottom line, the magnetic field should not have an effect on the post-merger frequency. So that is good from the point of view of determining the equational state. But there's still some question mark, because if we look at the paper from Shibata, Kyuchi, and collaborator, in their paper, they are a bit more pessimistic in the sense that the frequency of the peak remains the same, but the magnetic field has a sort of viscous effect on the remnant, and therefore it may dump very quickly the gravitational wave signal, and therefore may bring the peak below the sensitivity curve, for example, for advanced LIGO or even the Einstein telescope, making this detection even more difficult. So let me skip this. So since binary neutron star mergers involve nuclear matter, of course, you need really to take into account as an accurate model for the equation of state, and you also need to take account for neutrino emission. This is something that was not possible to do with our previous simulation with Whiskey and HD. Our simulation, as I told you, we're using essential ideal fluid or piecewise polytropic equation of state, but you really need to be able to use finite temperature tabulated equation of state coming from nuclear physics. And also you need to take account of neutrino emission in order to take into account about the evolution, for example, the electron function, and therefore the neutron matter composition, since this is very important, for example, for the kilonova counterpart of this match. So recently, very recently, we developed this new code, which is called the Spritz code. It's publicly available on Zenodo. It's also based on the Einstein toolkit. These are the 2 papers we published last year and this year, presenting the different methods. As I say, they can implement tabulated equation of state, finite temperature equation of state. Right now, we are running simulation of binary neutron star as well as neutron star black hole system with the Bombacci logo theta equation of state, which is a brand new equation of state that satisfies all constraints that come from accelerator experiments as well as from gravitational waves. So stay tuned for that. The method, the code implements also neutrino. At the moment, just via very simple leakage scheme. So it can take into account essentially mainly neutrino cooling, but it's not very efficient or accurate, let's say, to take into account neutrino absorption. And recently, we also had the implementation, thanks to a former student of mine, Beatrice Giudici, of 5th order method. We are Vinod Z scheme, but for the moment, just for the hydro part. So since I'm going out of time, let me go just to the conclusion. So magnetic fields can play a very important role in binary star mergers. So both from the point of view of short gamma ray burst and ejected matter. And I think Jay Kalilani is going to tell you more about this. The effects on gravitational wave signals seems quite minimal. As I say, the frequency of the merger peak does not seem to be affected, but there is discussion in the community about the amplitude actually of this peak. If magnetic field actually can dissipate essentially the signal so much that the peak will even go below the Einstein telescope sensitivity. If you want to have an accurate description of the dynamics of magnetic star merger, you also need to take into account not only magnetic fields, but also the effects of, for example, temperature, as well as neutrino emission. And this is why we recently developed this new code, which is Spritz and is publicly available on Zenodo. For the previous paper that I presented, the one we're done with Whiskey and HD, I just want to say that the gravitational wave signal initial data are available as supplemental material in our paper. So if you want, you can download the initial data and run the simulation via your code. And I just conclude with advertisement. If you're interested in the Einstein Toolkit, there's going to be a school and workshop this summer from July 26 and 30, and will be online. Will take place only in the afternoon or European time. It's mainly organized by colleagues in the US. And then, if you're interested to know more about gravitational waves from compact object binaries, Rosalba Pem and I edited a special research topic recently, and this is open access, and an ebook version is also available.
Thank you, Bruno.
Thank you for your time.
Thank you, Bruno. So it's time for questions. Let's take some questions for the audience. There are questions? Oh, here, Chris, go, please.
Yeah, I would have a question. I was always wondering if you have those neutron star mergers producing black holes, low mass black holes, possibly in a lower mass gap, what would be the spin?
The spin is typically around 0.7, 0.8. This is the spin of the black hole that is formed in these kind of simulations.
0.70, so high, very high.
Yes.
So it would be clearly distinguishable in LIGO data from all the other low spinning black holes.
So you're thinking essentially about binary star producing a black hole that then merge with another black hole, something like that.
Yes, exactly. I'm asking if that happened in a global cluster or any sort of cluster. And you have
yeah, you should be able to distinguish it because we'll have a high spin.
Okay, thank you.
Especially because of conservation of orbital angular momentum. It gets all the spin from the orbital angular momentum of the binary.
Very good, thank you.
Thank you. There is any other question from the audience? Oh, no. I have, look, I have many questions. I don't know which one I asked for you. But let me go through, maybe through main point. You are creating this, you have this magnetic field that anyway you have outside. All these configurations, these are very general. I know you care very much about the gravitational waves, but there is a string point that I think you should care a lot about, and is the short gamma ray burst. Because if you continue to try to explain systems like GRB 1708, 17A, all the way to the short GRBs that we knew, you will need to explain 8 order of magnitude difference in energetics. So you have to explain from a neutron star merger system which emits 10 to the 46 erg all the way to a system that emits 10 to the 54 erg. So I don't know how you're going to do that only using these kind of mergers. And the second question is,
okay.
Sorry, yeah, and the second question is, you at the beginning, you mentioned that you expect most systems to go through the channel of creating a black hole. So a question is, how what is the amount of mass that is ejected in these systems? And so you predict that the most of the population go through that channel. But if you use the RB 17, if you use, for example, LIGO population, the population of systems like GRB 17 or 17A should be very large. So is that okay with the prediction that all systems go through that channel forming a direct black hole, probably with very poor ejecta?
So answering to the first question. So if you want to have an accurate study of the, let's say, the emission of the gamma ray burst and the afterglow, this is something that you cannot do with just one code. So there is something that collaborators of mine, for example, Carlo is already doing, and some other work we also did, actually was also involved with Davide Lazzati, for example, is to take the results from binary star simulations, so get a realistic, well, realistic and accurate as possible description of the ejecta, and then to see how the jet propagates to this ejecta and try to understand the gamma ray burst prompt emission as well as the afterglow. As I said, in our simulation at the moment, in this simulation for neutron star black hole, we don't have yet the formation of a relativistic jet. That is mainly because we don't get yet the magnetically dominated region, possibly because of resolution, or maybe we should start, as other people do, just with a very large magnetic field from the beginning. And that's it. But then if you want to get an accurate description of the light curve that you get from the gamma ray burst, you cannot do this with this code, because you really have to go to much larger scales. So essentially what not just us, but other people are trying to do is to put the jet that may be formed from this binary neutron star merger simulation and evolve it with a different codes that take into account the jet that are produced by this system. Regarding the second question, so it's quite a complicated thing to do, but we are working on that. And regarding the second question, so in the case of GW17 or H17, according to observation, the mass of the system and so on, it's very possible that it went to this phase. So an hypermassive neutron star that survives for a few tenths of milliseconds and then collapses because of torus, because this will also be consistent with the observations that are in the kilonova emission, in particular the blue component, the one that is not very neutron rich. Regarding the other model, GW190425, that was very massive, and indeed the idea in that model went through this channel. So a very high mass system that essentially produced immediately a black hole, and therefore didn't have much ejecta, and this is also why we didn't see any electromagnetic counterpart. So these are the channels. This will be the channel for GW17 or 17, and this will be the channel for GW190425.
Okay. Thank you, Bruno. We have maybe a last question by Elias.
Yep. Hi, Bruno. Just a very quick one on the funnel magnetization issue. Sort of from your simulations, like, do you expect that the funnel would sufficiently magnetize on its own, or do you, like Ruiz et al., think you would have to put already some colloidal field there? I mean, they're basically playing with some different prescriptions on how to get the colloidal field in the funnel.
Okay, so let's say from a physical point of view, we expect that at merger, the magnetic field should be amplified of several orders of magnitude. There have been several simulations that show that at merger, you have the formation of what is called a Kelvin-Helmholtz instability. So essentially you have turbulence in the fluid. The problem that in order to fully resolve this turbulence, you really need to have very high resolutions. But if you do that, you should expect the magnetic field to grow up to reaching almost equipartition with the kinetic energy of the turbulent flow. And if you do that, I mean, you may reach a magnetic field that are large, like 10 to the 16 Gauss. This is something, for example, is discussed in this paper of mine in 2015. So what Ruiz et al. Do essentially, since they assume that the magnetic field should be amplified of several orders of magnitude, they start immediately with something very large. Very large means 10 to the 15 to the 16 Gauss, which is not so large to affect the spiral, but at least at the merger, you already have a very large magnetic field. So it's a sort of a trick if you want. Other possibility to use, for example, subframe models. There is one that was suggested by me in 2015. There are other models suggested by other authors. That is another possibility. If you don't do none of these, you don't have the capability to do this very high resolution that, as I said, they are incredibly expensive. As I say, the Future Tala, we're doing simulation with resolution of the order of 10 meters. The typical simulation that is done in binary neutron star merger is between 100 and 200 meters. So we speak about one order of magnitude larger resolution. So if you don't do any of these things, your magnetic field will grow just to one order of magnitude. So you start, for example, 10 to the 10, you get 10 to the 13. It is possible, maybe if you wait very long, since the disk is unstable to the MRI, maybe thanks to the MRI, maybe at a certain point you will see the magnetic field growing and maybe you get the amplification. But At the moment, we didn't see that in our simulation. So I think, I mean, we really need to take account of this amplification happens a merger or by using high resolution or something like a Supernova. Otherwise, just do like Ruiz et al. Do and just start with a magnetic field, large magnetic field since the beginning. The best, of course, will be the higher resolution because that will provide a more accurate result.
Thank you, Bruno. Thank you, Bruno. Thank you very much for nice talk and for the discussion. So let's move forward. Next speaker is Jay. Jay, are you ready? Here you are. Good.
Hi.
So when you are ready, just start. Yes.
Okay.
Yes.
So are you able to see my screen?
Yes.
Perfect. So thank you very much. Hello, everyone. My name is Jay Kalinani, and I'm a PhD student in physics at the University of Padua in Italy. And firstly, I would like to thank the organizers for giving me this opportunity. And today I'll be talking about some of the results from our latest binary neutron star merger simulations performed in GRMSD. This work has been done along with my supervisor, Dr. Riccardo Ciolfi, and our collaborators, Professor Bruno Giacomazzo, from whom you just heard, and others, Wolfgang Castan, Federico Cipolletta, Lorenzo Enocci, Andrea Pavan, Beatrice Guidici, Lorenzo Sala, Eduardo Giangrandi, and Alberto Guedin. So, as you all already know, that binary neutron star mergers provide a rich phenomenology to study gravitational waves, short gamma ray bursts, radioactively powered kilonovae, and as well as to gain deeper insights on the neutron star physics. And indeed, the very first detection of gravitational waves from the merger of two neutron stars, also known as the famous GW1708-17 event, in tandem with a short gamma ray burst, GRB 1708-17A, and an electromagnetic transient, 8020-17 GFO, has cemented the long-standing hypothesis connecting binary neutron star mergers with short gamma ray bursts as well as kilonovae. And this event indeed opened new doors to multi-messenger astrophysics with gravitational wave sources. But this event also left behind some open questions regarding the mechanisms and the processes that produce this short gamma ray burst, as well as the kilonova. And in order to address these questions, numerical relativity simulations of the merger process play a fundamental role. And in order to incorporate these crucial effects of magnetic fields, as you already also heard from Professor Giacomazzo, we should perform these simulations in GRMHD. Now, as also Professor Giacomazzo talked about this, for the dynamics, depending on the initial mass and the neutron star equation state, binary neutron star merger can lead directly to a collapse to a black hole surrounded by an accretion disk as a prompt collapse, or it could pass through a metastable neutron star phase, which lasts about, say, 1 second for a hypermassive neutron star typically, and much longer for a supramassive neutron star, and a more extreme outcome is a stable neutron star that never collapses. Now, according to the standard scenario, a short gamma ray burst central engine is given by this classic black hole disk system. But but we see also that long-lived neutron stars do remain a likely outcome of merger processes. So one of the open questions that our work tries to address is, can this metastable massive neutron star, or the so-called magnetar, act as a central engine to power a short gamma ray burst jet? Also, the kilonova of August 2017 can be modeled as a two-component one, having a blue component and a red component. And the origin and the mechanism that produces this blue component is still not very well understood. So the second open question our work tries to address is, can the magnetically driven post-merger ejecta coming out, pushed out of this massive neutron star remnant before it collapses to a black hole, act as a source of this blue component of the kilonova? So in this presentation, I will try to go over some of the basic ideas and concepts that come out of our latest BNS merger simulations performed in GRMHD. And something that distinguishes our simulation is this very long post-merger evolution that allowed us to gain novel insights on how the magnetic field evolves and how it affects the system in hand. So here on top, you see the merger process for one of our simulations, extending up to about 100 milliseconds. after merger. Here on the top is on the meridional plane, you see the rest mass density evolution, and here on the bottom is on the equatorial plane. And as in all the simulations I'm going to discuss, our simulations produce the merger outcome is a differentially rotating metastable supramassive neutron star expected to survive much longer than the simulation time span before collapsing to a black hole. Below, you see the meridional mass distribution on much larger scales of the order 3,000 kilometers for a different simulation that extends up to almost 250 milliseconds after merger. And so yeah, a quick word on our numerical setup. So we perform these simulations using the numerical relativity codes Einstein Toolkit and Whiskey MHD for binaries having a chirp mass that is consistent with that of the GW 1708 17 events and having mass ratios of 1 and 0.9. And we use the APR4 equation of state for the neutron star matter, and we develop this initial data for this our irrotational binary using the public code Lorentz. And finally, we add magnetic field to our neutron stars as internal polyidal fields, as was also discussed by Professor Giacomatto. And here, but we assume a bit higher field strengths of the order 1, 5, and 10 times to the power 15 Gauss. So first, let's look at the magnetic field evolution. So magnetic fields get strongly amplified due to different mechanisms in action. So at merger, first Kelvin-Helmholtz instability takes place in the shear layer when the two neutron star cores come into contact. And later on, magneto-rotational instability takes over as a dominant amplification mechanism. So on the left, you see we plot the wavelength of the fastest growing MRI mode over the grid spacing, and about 30 milliseconds after merger, we find that MRI is reasonably resolved everywhere. In particular, purple regions indicate that the MRI wavelength is covered by more than 10 to up to 1,000 grid points. And this gives us the confidence that the features emerging at later time and the future evolution, the MHD evolution is reliable, at least qualitatively. On the right, you see magnetic energy evolution for our different simulations. So one interesting thing that we observe by running longer simulations is this flattening in magnetic energy. Roughly, that starts roughly after 50 milliseconds after merger. Now, this is indicative that there exists like an upper limit for the maximum magnetization that can be achieved in such BNS mergers. Moving on, we then compare to study the remnant structure. We compare the match distribution on much smaller scales. So for two simulations, so here on the left you see a simulation which is non-magnetized, and that is we call it as B0. And on the right we have a simulation which starts with a initial maximum field strength of 5 times 10 to the power 15 Gauss. You see that the remnant has a nearly spherical core attached to a torus-shaped outer envelope for both for the non-magnetized as well as the magnetized case. But a few tens of milliseconds later, when the magnetic field has become dynamically important, we see rather a more isotropic distribution for the magnetized case, while the structure and geometry remains almost the same as for the non-magnetized case. So strong magnetic fields indeed do lead to formation of a dense cloud of material surrounding this neutron star remnant. Next, let's look at the rotation profile. So on the left, you see the the rotation curves for different timestamps for one of our simulations. So in general, the trend we see is that the remnant has a slowly rotating inner core and a faster rotating outer envelope, with the maximum frequency peaking around 12 kilometers. And for larger distances, this profile becomes nearly Keplerian. And another thing another thing we see is that in time, this central rotation frequency, or the core rotation frequency, increases at the expense of the outer envelope. On the right, we try to study the effect of magnetic fields on these rotation curves, and we find that for lower or zero magnetic fields have minimal impact on the rotation curve. while for the model that assumes a very high initial field strength, that is 10 to the power 16 Gauss, we see that there is a non-negligible impact on the Keplerian curve in time. Next, I talk about mass outflows. So on the left, you see the radial distribution of unbound matter with the radial distance on the x-axis and the time on y-axis, with the B0 model in the bottom panel and the B5E15 model on the top panel. So in addition to the dynamical ejecta, which is common to both and is not much affected by the magnetic field, and this dynamical ejecta is driven out by tidal forces and merger shocks, we see that substantial contribution by the magnetically driven post-merger winds for the magnetized case, which are indeed absent for the non-magnetized case. And on the right, I show in the meridional plane the rest mass density distribution for one of the simulations around 100 milliseconds after merger, and the corresponding magnetization plot for the same simulation. And we see that indeed this outflow, at least for the pink and white regions, is quite magnetically dominated. Now, we also observe that because of this dense cloud, we have the funnel along the spin axis, which is also gets baryon polluted. And this baryon pollution problem can be critical in the case for short gamma ray bursts, as it can hinder jet formation at later times. Next, let's look at the magnetic field lines evolution and the structure. So on top left, you see evolution of magnetic field lines close to the remnant. And indeed, we see, as also Professor Giacomo discussed, we see there's a strong amplification in the equatorial plane developing this toroidal field. And we see growing helical structure along the spin axis, developing a poloidal field. But later times, this field line structure gets rather disrupted. But when you look at larger scales, these field lines extend to more than 100 kilometers, and with an average poloidal strength of about 10 to the power 15 Gauss by the end of our simulation at 100 milliseconds after merger. And this has indication that there is indeed a global field that is developing in this case at 100 milliseconds after merger. Now, what if we go beyond 100 milliseconds? So in the recent simulation performed by Dr. Cholfi shows that if we go up to 250 milliseconds after merger, a jet-like helical structure might emerge thanks to the continuous winding action of the neutron star differential rotation. But this result is not always true for all the models that we do the simulations for. But in this particular case, we find that that a collimated outflow might break out through this baryon polluted environment, as you can see also in the bottom plot, where I show the time component of the for velocity. And these radial velocities reach for about 0.2 to 0.3 c. But this outflow does not seem to be compatible with that of a short gamma ray burst jet, because we find that the maximum achievable Lorentz factors are quite low, and the outflow that comes out is at least 3 orders of magnitude too heavy. So for our simulations, we find that this magnetar scenario is disfavored for producing a short gamma ray burst jet, and rather favors a black hole disk system as a favorable central engine. In another word, what if we want to go beyond 250 milliseconds? So indeed, we are at the end of the day limited by computational resources. So one of the recent works done by my colleague Andrea Pavan, along with Dr. Cholfi, what we do is we hand off the data from a BNS merger simulation to another code, which is called Pluto. And this acts as an initial data, and we perform special relativistic jet simulations. And so here on top, you see the rest mass density distribution, which is imported at around 110 milliseconds after merger. And this is also the time we, by hand, inject a top hat jet, which then evolves through this baryon polluted environment. And here we also include the effects of Newtonian gravity. And I would not go much in details of this paper, but this was just like a flash advertisement. I just wanted to highlight that these are the first kind of jet short-term Airbus jet simulation performed in a BNS merger environment, and results are very interesting. So in another work, we rather focused on the origin of the kilonova components that was accompanied along with the GW1708, 1709. So this kilonova showed can be modeled at least as a two distinct component kilonova, with having a blue peak peaking around UV and blue wavelengths. Associated with matter that is has velocities of about 0.2 to 0.33 and along with masses of about 2% of that of solar mass. And there's another there was a red component that peaked a few days later, and that is associated comparatively with much slower velocities and a higher mass. So the source of the red component is most likely the baryon winds arising from the post-merger, from the accretion disks that surround the black hole that is eventually formed after the merger. The source of the blue component still remains a mystery. So we consider the possibility that, we consider the possibility that the ejecta that was driven out by the massive neutron star remnant was magnetically driven, and this was one of the main sources behind the blue component of the kilonova. So to confirm our hypotheses, we analyzed the results from the latest simulation that goes up to 250 milliseconds after merger, and we indeed found ejecta velocities reaching of about 0.2 C and 0.2 C, and also the unbound ejecta masses also reach around between 0.1 and 0.01 and 0.03 solar masses. And these constraints are pretty consistent with what we also expect from the blue component of the kilonova. Just to quickly jump to a different, the technical side. So Professor Giacomato introduced our new. Yes.
Sorry, you have 3 minutes left.
Perfect. So just to, so I won't go into details. We have this new GRMHD code, which also includes a neutrino leakage. This code is called SPRITZ. So we are currently working on different elements of SPRITZ, and we are also currently performing different binary neutron star merger simulations. So this is one of the couple of simulations performed by my colleague Lorenzo and Oggi with using the SLY for equation of state. And yeah, so this is an equal mass case, and there's an unequal mass case. And here you see the rest mass density evolution, which forms a black hole, I think, at the end of the simulation. So yeah, that's all with SPRITZ. And another element that we recently implemented in SPRITZ is a new quantiprim scheme, which is called as reprimand. This was introduced by Castan et al. 2021, and this scheme is based on a root bracketing scheme similar to that of Brent-Dekker schemes, and it's proven how that it always converges to a solution. It also comes with a very strong error policy. And it's also implemented in a completely EOS agnostic way, and it is also publicly available on Zenodo along with an EOS framework. So the natural step was to implement this scheme in SPRITZ, which we did, and we performed a battery of demanding 3D GRMHD tests. So here, one of the tests we did was a neutron star with an extending, adding an extended dipolar field using a prescription of Moista et al. 2020. And we see that the reprimand scheme is able to handle low density, high magnetized regions rather well outside the neutron star. And on the right, you see another simulation test which considers a evolving a fishbone Moncrief black hole accretion disk. And here we also see that the reprimand C2B scheme is able to handle highly magnetized black hole environments rather well. So let me quickly summarize and also emphasize that GRMSD simulations of binary neutron star mergers are indeed play a fundamental role in to understand the physical and mechanisms that are involved in BNS mergers. And following this path, we performed many different GRMSD simulations, and we found that for the magnetized scenario, we do not find favorable outcomes as for it to be a shotgun jet central engine. While on the other hand, we do find that these post-merger ejecta that is driven out by from the massive neutron star before it collapses to a to a black hole, which are magnetically driven, can be a potential driver behind this blue component of the kilonova that we see. For future now we finally have a new GRMSD code Spritz, and we also implemented a robust C2P scheme, and our future steps would be to perform BNS merger simulations using this new C2P, as well as employing temperature and composition dependent equations of state, including Newtonian radiation, also having the fields extending outside to the exterior of the neutron stars, and also include neutron star spins. With that, I stop here. Thank you very much, and I would be happy to take questions.
Thank you, Jay, for being on time. So there is any question? Any questions from the audience? I don't see any questions in the chat. Yes, Chris, please.
I would have one, just being totally ignorant on that subject. I still would like to know, it seems like in your simulations, you naturally predict the collimation opening angles of the jets. Is it right, of outflows from the merger product?
I'm sorry, could you kindly repeat?
Yeah, it seems like in your simulations, you produce naturally collimation of jets, of outflows from your merger products. Is that right? How do they, what are those opening angles, and how do they compare with the measurement from opening angles in short GRBs? Are they totally discrepant?
Right, so if I remember correctly, we do find an opening angle of about half opening angle of about 15 degrees, and for one of the simulations. And this is marginally consistent with what we expect also from short gamma ray bursts. But
larger, is that right? It is larger. I mean, short GRBs would be about 5 degrees.
5 to 10. Yeah,
5,
I think
10.
this. I think for short, if I don't want to say something incorrect, but in my knowledge, yeah, we have a half opening angle for 5 to 10. So for example, you have for one of the simulations that we performed, when we inject this jet by hand, we take a half opening angle of about 10 degrees.
I see.
But yeah, so when we perform this kind of simulations, we do include, yeah, that. But for the simulation that we directly see from a BNS merger, I think it's about 10 to 15. I don't exactly remember the value.
Okay, thank you.
Elias?
Hey, Jay, great talk. Actually, you're just on the slide that I wanted to ask a question on regarding the blue kilonova correlation. I mean, in the simulation, you're not able to track composition, right? So do you have a way of making sure that the ejecta that you're looking at actually do come from the hot surface of the neutron star? Or can it also be ejecta that come from the disk and would not necessarily be blue?
That's a good question. We don't have a direct way of knowing of course, the composition of the masses. We only can infer from what we see as velocities, and also the masses. But what we see from the outflow is that it is indeed magnetically driven. So if there is indeed this magnetic push coming out from this from the axis, from this conical from the cone close to this vertical axis. So we indeed find that this is likely produced, very likely produced by it's magnetically driven. But yeah, we don't do one thing that is lacking from our in our simulations is the study of the composition. I don't know if this was enough to answer your question or.
Oh, that was perfect. Thank you.
Thank you. Thank you. I have a similar question, very, very similar, because in the usual picture of the evolution of the material leading to blue and red kilonova, what is the heating source? Is the energy released from the R process decay? Okay, and that injects about between 10 to the 15, 10 to the 16 air per grams. But if I take your numbers of the magnetic energy that you have, you will be injecting of the order between 10 to the 17 and 10 to the 20 ergs per gram. So this material in your case will be completely dominated by the magnetic energy and not by our process decay. So actually, whatever if you have our process or not, you don't care. I mean, is this correct? Even if you will add composition, you will not get anything different, I guess.
Yeah, I would agree, but I would okay, this outflow is definitely produced by the magnetic push that we see here. But yeah, I cannot be 100% conclusive that what could be a interplay when you also have neutrino effects and how it could affect the energies that we see. But in my opinion, definitely, even if we perform simulations that also include neutrino effects, we would definitely we expect at least to see this magnetic component that is providing this these energies.
Good. Okay, Jay. Thank you. Thank you very much for this very interesting work. So we move to the next speaker. Next speaker is Alexandra. So Alexandra, you're ready. So
okay, can you hear me and see my slides?
Yes. Okay, that's right.
Okay, cool. So my name is Alexandra Olejak, and I am PhD student under supervision of Chris Belczynski, who is one of the chairs during this session. And today I will talk about the formation and the origin of the first double neutron star detected collision, the event GW170817. So this talk will be summary of the article Belczynski et al. 2018 with the similar title, and it can be found on the archive. Here is the plan of my presentation. First, I will remind a few words about the detected double neutron star collision and tell a few words about the host galaxy located for the event. And then I will turn to the theory of the double neutron star formation and focus especially on the time delay distribution. I will compare the results of our simulations with the estimates given by LIGO-Virgo collaboration and also with the known galactic double neutron star population. So first, as all of you know, on the 17th August 2017, the first double neutron star collision was detected by LIGO-Virgo collaboration. And here are the estimated masses for the system under the assumption of low spins. The signal duration was about 100 seconds, and it was followed by the short gamma ray burst with the duration of about 2 seconds. And we were also lucky to detect the electromagnetic counterpart for the event. And thanks to the fact that the gravitational wave signal was detected by 3 gravitational wave detectors, and also in the gamma ray burst, it was possible to quickly localize the event And after about 11 hours after GW event, the first optical light associated with the collision was found. So yeah, the astronomical transient was localized about 11 hours after a gravitational wave signal in the galaxy NGC 4993, which is the nearby galaxy about 40 megaparsecs away. And it is an old and elliptical type galaxy where the star formation peaked around 11 gigayears ago. Yeah, the star formation peaked around 11 gigayears ago, and at that time it was at the level of about 10 solar masses per year. And it was estimated that the 50% of the stars in the galaxy were formed by 11.2 gigayears ago, while 90% was formed by 6.8 gigayear ago. And it was also found that there is a little to no ongoing star formation, and there are no expected young stellar populations in the galaxy. However, the more detailed spectral photometric and image analysis of the galaxy showed that there could be some possible little star formation episode in the history associated with some minor galaxy mergers. However, the total episode of this star formation could provide no more than around 0.4% of the total stellar mass of the galaxy. And as you can see, this is the plot from this paper Blanchard et al. 2017. And here's the star formation rate estimated for the galaxy and in the logarithmic scale. And you can see that there is this significant drop in the star formation, and current rate is barely negligible. So detection of the first double neutron star collision in this type of the galaxy, so the old and no longer star forming galaxy, was a kind of surprise for probably most of the people who deal with the double neutron star systems, especially the ones who do the population synthesis as we do. And for the reason which I will try to explain in a few moments, but first let me remind you the definition of the time delays. So the time delay is a sum of the time of the evolution of the system since the formation of two stars till the formation of double neutron star system, plus the time since the formation of double neutron stars till their final collision due to emission of gravitational waves. And yeah, as the neutron stars are rather the neutron star progenitors are rather massive stars. This the second component is usually the dominant part of the time delay. And in our simulations, we use this classic and well-known formula by Peters, 1964, to estimate the time to the merger. And yeah, it is quite a generic and known result that distribution of the time delays for double neutron stars could be fitted by the power law function with the exponent of which is approximately equal to -1. And as a consequence, the distribution is strongly dominated by the short time delays, and therefore it is expected for the double neutron stars to come mostly from the star forming regions. As for example, a galaxy that has its birth around 100 mega years would have its double neutron star collision rate of about 100 times larger than elliptical type galaxy with the same equivalent star formation episode that took place around 10 gigayears ago. So yeah, so maybe there were some other formation scenario for that system. However, first of all, it is worth to note that there is no visible globular cluster in the vicinity of the merger, which was reported by several studies. And yeah, but even considering that this system could form via globular cluster evolution or nuclear cluster, some other studies by Belczynski et al. 2018 showed that the rate for this type of galaxy, for all the elliptical galaxies, should be strongly dominated by the rate from the isolated binary evolution, as it is around 2 or 3 orders of magnitude larger than the rates expected from the globular clusters or nuclear clusters. However, at the same time, this rate is around 2 orders of magnitude lower than the rate and indicated by the LIGO-Virgo collaborations after detecting the first double neutron star collision. So, as you can see, there is some some problem with reconstructing the formation for such an event, and maybe it could be just a statistical fluke to detect the first collision with the elliptical-like galaxies. However, if we begin to detect more such collisions in this type of galactic, that could indicate that we have some problem with understanding our isolated binary evolution channel. And in order to check our time delay distribution and do some other tests, we took the known galactic population of double neutron star systems. And as you can see, here is the list of 16 known double neutron star systems in our galaxy, which comes from the field, plus 2 which come from the globular clusters. And as you can see, they can be divided into 2 groups. The first group of double neutron stars have rather low separation, and therefore also their time to the merger is estimated to be short, and they would probably merge in the next Hubble time. And the second group are the wide systems, for which the time to the merger was estimated to be sometimes much more longer than the next Hubble time. And the interesting fact is that the fraction of those systems with short time to the merger is equal to this fraction of the systems with long times to their merger. So it can be said that this is 50% to 50% fraction. And we wanted to check how would the results of our population synthesis studies using StarTalk code would compare with the results for our galaxy. And to do so, we need to build some sort of model of equivalent-like galaxy. And to do that, we adopt some simple model of star formation for Milky Way, which, in other words, we assume that the star formation for our galaxy was constant during last 10 gigayears. And among the simulated systems, we took double neutron star binaries that are currently present in our galaxy, so they did not merge till the current time. And we also checked if one of the neutron stars could be any pulsar of any type. And to do so, we adopt those distributions of the lifetime for the radio and recycled pulsars, which we obtain based on the observations of pulsars And we check if the time of the life of our neutron star is shorter than the given pulsar, the pulsar time estimated, generated from one of those distributions. And also for the recycled pulsar, we check another condition for the accretion. And this is how we obtain some probe of the double neutron star, galactic double neutron star systems that could host at least one pulsar. And yeah, as the result, for our standard models, most of our standard models, we were able to reconstruct this fraction of 50% to 50% of short to long merger time double neutron star systems. We also did another test. We tested many physical models. We took around 20 physical models where we applied wide distribution of the natal kicks for the neutron stars. We took the very high natal kicks as well as the assumption of zero natal kicks, which is quite unphysical, but we just want to test also those extreme variants. And we also did several assumptions to the common envelope efficiency and to the stable mass transfer. And we test two things. First, for the given physical model, we test how the estimated merger rate, galactic merger rate would compare to the observational rate for double neutron star collision for our galaxy in the unit per mega year. And the second thing, we estimated the merger rate for all the elliptical galaxies in our local universe. And we compare this rate with the rate given by LIGO-Virgo collaboration in the unit per gigaparsec cube per year. And yeah, it is worth to note that this number is the number which was announced after the collision, and now it dropped a bit, but still it is a high value and the problem still exists. And our results are that for our standard models, we reconstruct well the galactic Milky Way double neutron star rates. However, at the same time, the rates for the cosmic rate, with the assumption that all the rates comes from the elliptical galaxies, is very low, and it is not within the range given by LIGO-Virgo. While those models, which we assume a bit unphysical, but because they, for example, they assume this non-physical value of common envelope efficiency or zero natal kicks for the double neutron stars, then those models, they do reconstruct this cosmic rate given by LIGO-Virgo for elliptical like galaxies, but at the same time they give much overestimated rates for the comparing to the rate estimated for galactic population of double neutron stars.
Alexandra, 3 minutes.
Okay, yeah, so this is briefly what I said. We also do some comparison of how the distribution of time delays looks for the different physical models. And yeah, it is the same that our standard models are the distribution of time delays for our standard physical models fits well the galactic distribution of the merger times of double neutron stars, while these models for unphysical models, which reproduce the LIGO-Virgo rate, do not fit well the observed double neutron star time merger distribution for galactic population. So yeah, the conclusion is, as I said, we don't know if this first detection of double neutron star was just a statistical fluke. However, if we continue to detect this sort of collisions in similar type of galaxies that there are no visible star formation episodes, then there is a chance that, for example, we didn't check well enough our parameter space, and we need to do some other parameter study in order to find a model that would at the same time reconstruct well the LIGO-Virgo rate as well as the galactic population of double neutron stars. However, if we won't find this model, that would indicate that maybe there is some more serious problem with understanding of our binary evolution, and maybe it demands some major revision, or maybe we need to assume that there is some other different formation scenario that plays a role in the formation of double neutron stars mergers. Okay, thank you for attention.
Thank you very much. We now have time for questions or comments. There is one for her. Please go ahead.
Okay. Thank you, Alexandra, for this presentation. So many doubts about this thing. It's not my field of research, but if I, from the statistical point of view, what is the chance? What is the probability that we have that GW17 or 817 was in an elliptical galaxy? I mean, from your calculation, it's 0?
I would say that it is like 1 to 100. So
1%.
Yeah, about 1%. Yeah, it was. I think it was shown somewhere here. Yeah, because this distribution of time delays follows this relation of power law. So yeah, it is barely 1%. I would say.
1%.
So, you know, we have one of the most amazing events that was detected by LIGO. We have most stars in binaries, and we cannot reproduce that event. We can do black holes, no problem, but we cannot do double neutron star in a because this is a very old elliptical galaxy. This is the key issue. We cannot do that. And our models do reproduce everything about galactic neutron stars. They reproduce short GRBs, but we cannot do that.
There is in one of your conclusions, you say that probably if we let's assume that reported detection is fine. Okay, we believe in that. Okay.
Yeah.
So
we believe, of course.
Okay. I'm not so sure. Okay, but that's okay. That means you should change something without changing the entire field of astrophysics. Okay, without changing all the stellar evolution that we know for decades. Okay, all the knowledge that you have gained for decades. What is the physics that you should change, that you think you should change, and that you can accommodate that without damaging the entire astrophysics?
Okay, so I have one candidate which was already discussed during this session. So maybe it is the case of stability of mass transfer. As we, for example, there are more and more works that shows that if we apply more stable mass transfer in the formation of double compact objects, for example, for black holes, also the time delays would the distribution of time delays would change and would be dominated by longer time delays. So maybe we should check this thing, that
will be dominated by the stellar evolution part and not by the gravitational wave shrinking. This is what you mean?
Yeah, yeah,
okay.
This is what I mean.
Actually, that would
maybe
be
Chris,
I think it would be if you or anyone who's working on a stable mass transfer would quantify the delay time for that channel, because I don't think that was done. So that's a really open project that one of you should jump on and just get it done and publish it. Because I have no feeling how much that would change things. Yeah, that's exactly.
That is interesting.
Yeah. Yes, please go ahead.
Yeah, just a quick question. So do I get it right that the time delay distribution is not dependent on metallicity?
Yeah, maybe I didn't check it properly, but I think it is rather the case that after the common envelope, the systems get rather short separation. So I think the metallicity doesn't matter for the time delay distribution. It matters only for the amount of the merger rate.
So pretty much the T2 - 1, T2 - 1.5 is very generic. It comes from initial distribution of separations as processed by Peter's equations. That's a very generic outcome of population status models, at least for common envelope channel. Very generic.
Okay, thank you.
So you need a broken power law, right?
Yes, that would be great. Or maybe it was a fluke, or maybe I would hope Clary would have an answer from global clusters. So I think if there is no more questions or comments, we can switch to global cluster formation of double neutron stars. Maybe the answer will come from that side. Olka, could you please stop sharing the screen, and we'll ask Clary to share hers.
Yeah, sure. Just a second. Let me share my screen.
Go ahead.
Okay, can you all see my screen?
Yes, we can. Thank you very much. Please go ahead.
Okay, thank you. So my name is Claire, and I'm a PhD student at Sierra at Northwestern University. And I will talk about the merger rates of both binary neutron star and neutron star black holes from globular clusters, since the dynamical evolution of these two groups of compact objects are closely connected. So I will have an answer to the merger rate from globular clusters, but so spoiler alert, it will not really match the LIGO-Virgo estimates. Anyways, let me get started. Globular clusters are found in every galaxy. For example, in large elliptical galaxies like M87, there can be 10,000 globular clusters. There are about 150 in the Milky Way. Many of them live in the galaxy halo. Some are close to the galactic bulge. And globular clusters are old and massive stellar systems that have roughly 1 million stars. They form at about the same time as the galaxy. And their half-mass radii are only about a few parsecs. So they are very compact and have very high densities around the center, as is shown in the picture here of a random globular cluster in the Milky Way. They potentially contain a large number of compact objects, including black holes and neutron stars. Indeed, because globular clusters are massive and dense, stellar encounters happen frequently in them, leading to the formation of exotic objects such as millisecond pulsar binaries, low-mass X-ray binaries, and binary black hole mergers. It is now well known that clusters produce these various sources at higher rates per unit stellar mass compared to isolated stellar evolution alone. So even though only a fraction of the total stellar mass in a typical galaxy is found in globular clusters, they may contribute significantly to the total population of various exciting phenomena. But as you can see, I don't have a picture for neutron star binary merger here. And I will show you why that is. So just to remind everyone, since cluster dynamics can boost the number of many exotic objects, you might think that it may also produce many neutron star, and neutron star black hole mergers. So there are some suggestions that neutron star binary mergers from clusters can take up to 10% of the total mergers. For example, clusters can produce all potentially observable binary black hole mergers. The first detection of a binary neutron star merger, as was mentioned by Alexandra as well, was in an old non-star forming galaxy, which means it might be in an old globular cluster. And about 10% of short gamma ray bursts have large offsets from the galactic center, which suggests that they may originate from dynamically formed compact object binaries, or from tidal capture or collisions of compact objects. And what's more, the only binary neutron star known in a cluster has the similar eccentricity and orbital period to a few binary neutron stars observed in the Milky Way field, suggesting that those binary neutron stars in the field might be kicked out from clusters. And the recent detection of GW190814 showed that it has highly asymmetric masses, and the lower mass object falls into the lower mass gap, which are hard to produce with isolated binary evolution. And in the following slides, I'm going to show that despite the boost from dynamics and all these suggestions, globular clusters do not produce many binary neutron star mergers or neutron star black hole mergers. To study neutron stars in globular clusters, I use the cluster Monte Carlo code, also called CMC. CMC has been developed by many people from our group for about 2 decades now. It has a star-by-star realization where n particles represent n stars in a spherical potential. The star's initial positions and velocities are in general sampled from a distribution, and the masses of the stars are drawn from a realistic initial mass spectrum. And CNC has all the relevant physics for cluster evolution, including two-body relaxation, strong 3- and 4-body interactions, and single and binary star evolution. It can simulate massive star clusters and is much faster than direct n-body simulations. A typical cluster model takes about 1 to 2 weeks, and depending on the mass of the cluster, it can take even shorter time. So this allows us to simulate a large grid of cluster models in a relatively short time scale and explore different globular cluster initial conditions. And what about the formation and retention of neutron stars in clusters? Neutron stars can be formed in core collapsed or electron captured supernova. Which one happens depends on the initial mass and metallicity of the progenitor star. So stars at around 8 solar mass are likely to reach electron captured supernova, but the more massive stars will undergo core collapse supernova. So X is shown in the figure here. During electron capture supernova, electron degeneracy is reached, and magnesium and neon start to capture the electrons. The star then loses electron pressure and collapses to a neutron star. Electron capture collapse can also happen to an oxygen neon magnesium white dwarf if the white dwarf is in a binary and is accreting mass. So that is accretion-induced collapse. For both scenarios, the oxygen neon core will collapse to a neutron star if it's more massive than about 1.38 solar mass. And the good thing about electron capture supernova is that its explosion energy is far smaller than core collapse supernova. So newly born neutron stars from electron capture supernova receive smaller natal kicks. In CMC, the velocity dispersion of this kick is assumed to be 20 kilometers per second, while neutron stars from core collapse supernova have 10 times larger natal kicks. The small natal kick here is significant for the retention of neutron stars in globular clusters. That's because the escape speed of a cluster is less than about 100 kilometers per second. So most of the neutron stars formed in core collapse supernova will escape at the time of formation. And on the other hand, neutron stars from electron capture supernova are very likely to be retained within the clusters. And I searched for neutron star binary mergers from a large grid of CMC simulations. These simulations span a wide range in the initial number of stars, metallicities, sizes of the cluster, and the distances to the galactic center. The blue dots in the figure shows the final properties of all the simulations, and the black circles show the observed properties of Milky Way clusters. The x-axis is the ratio between the core radii and the half-light radii. And you can see that these two sets of dots overlap quite well. So one nice thing about these simulations is that the total number of simulations is roughly the same as the total number of globular clusters in the Milky Way. So these cluster simulations are representative of the present-day Milky Way globular clusters. And as was mentioned in the beginning, in globular clusters, the dynamics of neutron stars and black holes is coupled. Because of mass segregation, where more massive objects tend to sink further to the center of a cluster, black holes dominate cluster centers. Dynamical encounters between black holes and other stars can then heat up the cluster and actually prevent neutron stars from moving to the center if there are many black holes. For example, in this plot, on the right is a 2D projection of a typical core collapse cluster. There are few black holes in this type of clusters, and the neutron stars concentrate at the center. On the left is a typical non-core collapse cluster. This cluster has many black holes, in this case 116, and the neutron stars are prevented from sinking to the center. So here the red circle is the core radius. So a decreasing number of black holes correspond to more concentrated neutron stars from the cluster center. And since the core is the densest part of a cluster, and most dynamical interactions happen here, fewer black holes also means more encounters for the neutron stars. Typical globular clusters can have as many as 100 black holes retained, as is similar to here. And in these clusters, neutron stars are further out and don't have many chances to form binaries with another neutron star or black hole. And whether a cluster becomes core collapse or not is decided by its initial size, given that all other initial conditions such as the initial mass function and the binary fractions are the same. Clusters with small initial virial radii or its size process their black holes faster and thus will kick out most black holes in a few gigayears through dynamical encounters. As is shown by the blue curve in the lower panel here, so you can see that the black hole numbers is decreasing. And in the corresponding core radius plot up here, the core is actually shrinking. The core radii of these clusters decrease with the decreasing number of black holes, as was just said. And most of the neutron star dynamics kicked in after this time scale of roughly several gigayears when most of the black holes are removed. So how many neutron star binary mergers are there in the clusters? This plot shows all the neutron star binaries that merge within a Hubble time in 144 simulations. The red circles are neutron stars formed from dynamical interactions, and the green circles are neutron star black holes also formed from dynamical interactions. As was mentioned, neutron star dynamics is most frequent at late times of a cluster evolution. And so most of the dynamical mergers also happen at late times, and they can potentially be observed by LIGO and Virgo. But it is also very obvious from this plot that the total number of mergers are small. So remember that neutron stars only occupy the centers of core collapse clusters, and only around the center can neutron stars get plenty of encounters to form binaries. And in the Milky Way, about 20% of globular clusters are core collapsed, which is just not many. So the overall total number of neutron star binary mergers from globular cluster is low. And dynamics doesn't play an important role in enhancing the neutron star, and neutron star black hole merger rates. Here shows the merger rates of neutron star binaries from clusters as a function of redshift. The merger rate is about 0.01 to 0.07 per gigaparsec cube per year in the local universe for both systems. And the LIGO-Virgo merger rate estimate can be as large as about 1,000 for neutron stars, and about 150 for neutron star black holes from the latest detection of 2 neutron star black hole mergers. And the comparison between these rates are shown in the inset here. So note that this is the old rate still from the second runs of LIGO-Virgo. So the number of neutron star binary mergers are about 10 to the 4 to 5 times smaller than the LIGO-Virgo estimates. This shows that globular clusters are not a good place to look for neutron star binary mergers. And to explore the extreme upper limits of the number of neutron star binary mergers from globular clusters, we also ran an extremely optimistic model. This model has a typical Milky Way cluster mass, but have very small initial size, so it core collapsed. The initial mass function is also cut at 30 solar mass, with unrealistic large natal kifs for black holes of about 2,000 kilometers per second. So the model is depleted of black holes. And in contrast, the neutron stars all have small natal kicks, so many of them are retained in this cluster. And this model is trying to mimic the famous M15 globular cluster, which is core collapsed and has the only confirmed neutron star detected in a globular cluster. And even with these extreme initial conditions, and assuming that all the clusters in the local universe are like this extremely optimistic model, the merger rates for the neutron star binaries from clusters barely get close to the lower limits of the gravitational wave detection estimates. And I should emphasize that observations have shown that only about 20% of globular clusters are core collapsed, and their initial conditions are very unlikely to be this extreme. And last, some uncertainties might increase the number of merger. For example, tidal capture of neutron stars with other stars may become neutron star, or neutron star black hole binaries through subsequent exchange interactions. Clusters may retain a bit more neutron stars, given an even smaller neutron star natal kicks from electron capture supernova. Although this effect will be negligible since the cluster escape velocity is already many times larger. And massive and already disrupted globular clusters, which we don't observe at the present, may also contribute to the increase, but not by much. So
wait 3 minutes, okay?
Okay, thank you.
Thank you.
So the uncertainties will not give a large increase to the merger rates from globular clusters. And even taking all extreme conditions and uncertainties into account, globular clusters will not be the dominant source for neutron stars, and neutron star black hole binary mergers. So this is my last slide, and I will leave this plot as my conclusion. Thank you.
Thank you. Thank you very much for that insightful talk. We are now open for questions or comments from anyone. But before people decide on a question, I would have a comment that this is becoming a bit problematic issue. We have this amazing event, and I'm going to repeat that, and we don't know how it formed. So it seems like, a lot of people are working on that. It's not being really talked aloud about this issue. People kind of put it under the table, but it is an issue.
Yeah. Even during our group meeting today, we start to talk about this again, even though we know like globular clusters don't produce much, but we know that there is an issue of like matching these merger rates. And we are starting to think if there's any other way to like produce this through dynamics.
So I have actually a proposal for you. When I got that idea during your talk, when you mentioned neutron star formation, you mentioned electron capture supernovae and core collapse supernovae. Those are most natural way to make neutron stars. But there is also a different way. You can have a white dwarf. You have a lot of CVs in global clusters, right?
Right.
You could have white dwarf accreting from a star and going accretion-induced collapse with almost no kick, forming a neutron star. You form two such neutron stars, and then you exchange. And you form a double neutron star, closed double neutron star. Have anyone ever checked that type of channel, formation channel for double neutron stars in clusters?
No, I don't.
Not aware of it. Yeah.
Yeah, I don't think so.
Yeah, Chris, that was exactly what I was going to say, something similar.
Sorry.
Because my question is that, in fact, going to this line, I mean, in your calculations, you are not producing this. You're not starting from the binaries. I mean, the stars are catching by chance in the cluster.
Yeah.
Well, no. Well, I'm gonna.
I mean, they get dynamically bound.
They do, but I think they do have some primordial. Clara, you do have some primordial binaries in clusters.
Yeah, we have. So for this set of models, we assume 5% primordial binaries. So there is primordial binaries, but that doesn't play a big role. I mean, it's just because the percentage is so low. Unless we know that the primordial binary percentage is high in clusters, then we can maybe tweak the rate. But currently, the common understanding is just that there are about 5% primordial binaries in globular clusters.
Yeah, so that's a good channel to test. That you form the neutron stars separately and then you catch them, they get bound dynamically.
Or you actually know what? Or I would actually do, I've seen simulations with 80% of initial primordial binaries, or I would even say with 100% binaries in a cluster, all stars in binaries, primordial, and then try to do as many accretion-induced collapse neutron stars as possible and see if I can even touch the bottom of the rate of double neutron stars. And then if you can exclude that, I mean, we're done. I don't know how we do it then.
Yeah, 100% binary will definitely produce more of these systems, but there's also another constraint that is very strong for globular cluster. That is the number of millisecond pulsars that we know very well. Yes. So that is the absolute upper limit that we cannot pass. And if I think 100% binary fraction will definitely produce too many millisecond pulsars.
I see. I didn't realize that. But you're right. You're right.
Yeah.
Well, anyway, as a proof of principle, I would do such a study and show that even breaking a millisecond pulsar limits, I cannot do what LIGO is giving us. That would be, I think, a challenging paper for all of us to read.
So the probability that you are getting from this is as low as the false alarm rate.
Yes.
Oh yeah, I didn't realize that, but yes, the rate is very low.
Okay, any other comments, any other questions from anyone, please? Okay, if we don't have any more questions, we're gonna move to another talk. We're gonna go to, Clary, yes, you already did shut your screen off. So we go to Elias and to exciting prospects of potentially telling apart neutron stars and black holes in a lower mass gap, which is a very exciting issue these days. Elias, please, floor is yours. We cannot hear you yet.
Oh, is it working now?
Okay,
Thanks for the kind introduction. Just a little disclaimer. I'm currently in Colorado and my connection turns out to be a bit shaky. So in case I'm kind of intermittent already, sorry for that. So as Chris was already mentioning, I'm going to talk a little bit about a potential way to distinguish neutron stars from black holes in lower mass gap mergers. In particular, I'm going to invoke a signature of fast ejecta in order to facilitate this. So just to recap what
Elias, I think we have
we've
lost
already heard in
you.
several parts, especially if we look. Oh, you have lost me.
No, now we back now. You're back.
Yeah,
you're back.
Very, very sorry for that. The connection here is quite shaky, unfortunately.
Go ahead.
So, as we have heard already in great detail from Bruno and from Vijay, gravitational wave part, but we also have the kilonova afterglow produced basically by heating from the R process and from a short gamma ray burst that we could potentially form by launching a jet from like the remnant black hole disk system, or potentially also from a magnetar. And so
maybe he should switch off the camera.
kind of say we were to merge. Sure. Does that help?
Maybe, let's see.
Okay. In the case of high mass mergers, so this is when I make the stars much heavier than like 1.4, collapse into a black hole at merger, and I'm going to get this black hole disk system. And the interesting thing is, as Bruno was already pointing out, the 1904-25 event kind of fell directly into that mass range. If we open up that paper and we take a closer look at the allowed masses, what we're going to find is for the light companion, and for the primary, we can go up to 2.5 solar masses. The interesting thing about this is that this neutron star is kind of on the upper end of what is principally allowed. So if you think about 170817 and you invoke that this thing actually collapsed to a black hole, then you can show under some assumptions that the maximum mass for neutron stars is about 2.3 solar masses. And so if you look at this, in principle, that would include that 1904-25 could also have been a black hole neutron star system. And so it's kind of an interesting thing to say, well, how can we actually distinguish the two, like the black hole from the neutron star? And in general, even disregarding that particular event, we could do this if we had perfect knowledge of the gravitational wave signal. The reason is that black holes do not tidally deform. And so when you look at the phase shift up to merger, you would actually see a difference between the two systems if we had perfect signal to noise. However, in practice, we don't have this. We only have a signal, even for the black hole neutron star mergers that they announced this week or last week, we have a signal to noise of only like 10, 15 or so, which is not sufficient to do this. And so we need another window, another kind of way to look at the system and to make this choice. And so what we can do is we can ask, well, if the gravitational wave signal is inconclusive, would a potential detection of an electromagnetic counterpart tell us if we had a black hole or a neutron star? That's exactly what I want to focus on. But before we can do this, we have to kind of think, where is it actually reasonable to expect that the two systems would overlap in a way that if you had a binary system and you would make the primary heavier and heavier, at some point you would collapse to a black hole, simply because even when you add spin, you would not be able to support a neutron star from just collapsing under its own weight. And you can actually compute the line and parameter space in terms of effective spin of the binary and the mass ratio. That's something that I did last year. And you can delineate where the systems fall. For example, you can say if the star is too heavy, you would have a black hole in the system, and if not, you would have a neutron star. And kind of that motivates the region in which you would really look for this particular comparison. This is really where we have to choose the systems, because there we can naturally have neutron star, and black hole neutron star systems coexisting, so to speak, if we want to simulate that. And now what I did is I basically set up initial conditions for numerical relativity simulations using GRMHD and all of that. And the interesting thing is now you can cross this line that kind of distinguishes a neutron star primary from a black hole primary. We can initialize those systems. And you can see that these simulations incorporate neutron stars with masses up to 2.4 solar masses and spins up to 0.5 in dimensional spin. That's almost 1,000 hertz. And this is one of the heaviest and one of the fastest spinning neutron stars ever to be simulated. So it's a really challenging simulation. If we have questions later, I can tell you actually how that works, but it's really interesting that that can actually be done. And then when we do this, so on the top here, I'm showing kind of what happens directly at merger in terms of the rest mass density for black hole neutron star. And so what will happen for this particular combination, it's the high spin case. So we're merging a 2.4 solar mass neutron star with a 1.2 solar mass neutron star. And now the kind of secondary is tidally disrupted. You see this tidal arm flinging out, and you see that most of the matter is being accreted onto the black hole. If we compare this with the neutron star case, it's really interesting. You see that the second arm develops. And that's cool because that arm is not necessarily tidally driven, but it's kind of driven by a spin up of the primary star at merger shortly before it will collapse to a black hole. But otherwise, if you just compare the top and the bottom rows, you see that it looks surprisingly similar. But the main difference is really the secondary arm. So that's what kind of distinguishes the black hole neutron star merger from the neutron star merger. And it's just something that happens directly at the merger itself. You can then play this game and you can ask, well, is this kind of a feature that always happens? So you can vary the spin of the system. You see that even now the secondary arm is moving out faster. Just if you look at the distance that it has covered, you can ask what happens if you exchange the equation of state, because tidal disruption depends mainly on how big the star is. So you can use small stars, you can use large stars. Doesn't matter, you always get this secondary arm, but only in the neutron star case. So that's like a really unique feature that only those systems would exhibit. And then you can ask, well, if you think back to the talk on the long-lived remnant, in this system, really what you get is a black hole disk system. And if you assume that most of my kilonova would be driven by the disk itself, if we had different disks, the systems would clearly be distinguishable. Just if you had basically, could say you had a kilonova or you didn't have one, in the case in which you had a low disk mass. Now, what turns out to be the case here is that these systems have identical disk masses. And this is because since the neutron star is tidally disrupted, for the disruption, it doesn't matter if the tidal field is sourced by a neutron star or by a black hole because they have the same gravitational mass. And so really the system in terms of the kilonova itself is completely indistinguishable because after merger, you end up with the same black hole and the same disk. And so you will end up with the same evolution later on. So the really distinguishing feature is only the secondary arm that you get at merger, which was a little bit surprising in that sense. And then when we look closer at this secondary arm, we can actually look at the properties of the mass ejection. In particular, we noticed already that the ejector kind of seemed to move faster because they had covered a larger distance. If we bin this in terms of the velocity, what we're going to see is that actually the secondary arm picks up a very, very high velocity, but only for this neutron star case. So there's really a clear distinction between having these fast ejecta and not having them in the black hole neutron star case. Just if you look here, for example, in the zero spin case. However, interestingly, if you have very high spin on the primary, the systems almost become indistinguishable if you just look at the velocity distribution. What is important to point out here, though, is although we have these fast ejecta, they're very kind of small in terms of the total mass that you eject. It's less than 10 to the -5 solar masses in all cases. Now, what's actually so special about this, about these fast ejecta? And the thing why they're interesting is because they give you a distinct signature that's different from the standard kilonova. In particular, if you have fast material that shocks the interstellar medium, you can produce an X-ray and a radio afterglow. That's a model by Kenta Hotokezaka and earlier from Piran. And you could have that if those fast neutrons that are in the material move so fast ahead of the kilonova itself, they will not partake in the R process. They will just beta decay that provides additional heating and has been suggested to provide a neutron-powered kilonova precursor, which would happen on a time scale of about an hour or two after the merger itself. So this is really distinct from the standard kilonova signal that you get. And this particular model has been kind of received some attention, especially the X-ray and radio afterglow, because it was expected that for 170817, if you had fast ejecta, about 3 years after merger, you should see a rebrightening in X-ray and in radio. And indeed, people have now seen a rebrightening in X-ray only. And there's kind of the open question, will they also see a rebrightening in radio that would really kind of be the smoking gun for the fast ejecta, or is it just fallback matter? In that case, we would only see X-ray and the radio would never start to appear. That's something that, as far as I understand, we might know by the end of the year or early next year, but it's kind of an interesting prospect for this material. One thing to say for the black hole neutron star, for the cases we consider to tell them apart, is that because the material is so few, the observation prospect is actually quite low, simply because if you plug in the numbers into the same estimates that you could use for 170817, you would need about 10 to the minus 4 to 10 to the minus 3 solar masses. And that is assuming that the system would be closer than the actual 1904-25 event was. So in that sense, it's theoretically possible to tell them apart by their ejecta, but it's observationally challenging. And finally, before I conclude this talk, I wanted to make one more comment, and that kind of picks up on what Bruno was telling earlier on the ability of the system to potentially launch a short gamma ray burst, because we can actually ask ourselves what happens after the merger of the system. So when I disrupt, if you just look at the bottom panel, there you see nice density evolution, the evolution of the composition and temperature, and you can see as the neutron star is disrupted, you form this accretion disk, and over time you will end up with exactly the same situation that Bruno was describing for the binary neutron star, just that here you kind of miss out on the uncertainties of magnetic field amplification simply because you don't form a remnant. So in that sense, we can actually accurately study the system and put all the required physics in, even though there is no advanced neutrino kind of scheme. I'm also just using the leakage. The disk is so cool that that's perfectly appropriate to do. So really here we're capturing all of the necessary effects. And then what you see is that over time, because you have the MRI being active in the disk, you're going to grow poloidal field, and you're also going to amplify the toroidal field. And so over time, this field will grow. And then the question is that sufficient to eventually produce a jet or not? And as we have already heard, the main issue with this is that kind of the funnel in most simulations doesn't clear, except for example, for the black hole neutron star case, as done by Pascalidis, or also by a recent study by Milton Ruiz. If you put initially poloidal field in the funnel by basically tweaking with your initial conditions, you can produce a jet. Otherwise, it said you cannot produce a jet. And now the interesting thing that I found was when you take the system and you evolve for a really, really, really long time. So this is up to 350 milliseconds, which is like 10 times longer than the images Bruno was showing. You see that there is a continued magnetization building up in the funnel, because the funnel begins to eventually clear and the magnetic field continues to be amplified. And so we actually do see that the funnel becomes magnetically dominated. It just takes really, really long. In fact, it would take even longer if you do the estimate than at the end of the simulation. So there's still no jet, but there's very clear inflow and very clear magnetization just propagating upwards. And you can actually kind of try to estimate this or try to understand this a bit. And then when you look at the magnetization of the funnel or just the magnetic energy, you see it takes about 200 milliseconds after the merger just for the growth to eventually set in, and then it even slows down and it grows at a lower rate. And that's perfectly consistent with recent simulations of like toroidal field and accretion disk, simply because a toroidal dynamo is a very, very slow process. So to me, at the moment, it's not clear if for the eventual jet launching, also in the binary neutron star case, it's literally the field at the merger that you need, or it might just take a very long time for the disk to eventually produce that field. And then maybe you just only launch the jet after like 800, 900 at much higher resolution. With that, let me conclude the talk. I've tried to give you an idea that fast ejecta might be a very interesting tool to distinguish neutron star from black hole neutron star mergers in the lower mass gap, simply because they feature fast ejecta. It turns out that fast ejecta will be the signal rate that would also be helpful if you don't have this in terms of the difference. And so with that, let me conclude. And I hope that the connection was good enough so that you could hear most of the talk. Thank you.
Thank you very much. We heard about 80% or 90%, but we got your conclusions on a screen. And I think what you just said summarizes nicely the results on black hole neutron stars and neutron stars mergers. So that was very insightful. And it was actually a good summary, I would say, for entire session for today and for Monday. Actually, we were supposed to have one more talk on primordial black holes, on something even more exotic than we have talked so far about. But I don't see the speaker. I have emailed him a couple of hours ago, and it seems like primordial black holes are more elusive than I even thought. So we don't even get a speaker on them.
They even escaped the Zoom call. I just closed the.
You can keep your screen up. Actually, why don't you put your summary? Your summary is good.
Presentation, just hoping that the connection will be a little bit more stable.
Yeah, but put your screen, share your screen with your summary. It's a good slide.
We have two questions. It was first Bruno and then Jay.
Jay, please go ahead.
Okay. Hi, Elias. Thank you for this very nice talk. I have two very naive questions. One is, if I missed this, how did you produce your initial data for these both neutron star black hole and neutron star binaries? And I also would probably say the second question as well. So you mentioned about this fast ejector. So I assume this is a subcomponent of the dynamical ejector that comes out. So is there a way to distinguish, or are they, or another way, are they similar, or fast ejector and dynamical ejector, or is there, are there any differences? Thanks a lot.
Okay. Sure. Let me ask the first question first. So we have developed a new initial data code that was mainly led by Jens Papenfort. The code is public, so you can actually download it on the CADETH website. And what this code can do is it can produce high spin binary neutron star and black hole neutron star initial data in the XCTS initial data framework. And so it's really that initial data code that enabled the simulations. Otherwise, we would never have been able to produce neutron stars basically close to collapse and close to breakup in terms of spin. So there was quite some development going on for the past 2 years on the initial data side. The simulations themselves are done with the derived version of the Illinois code. It also uses high order, basically the same stuff that you guys have implemented now. And in that sense, you really have kind of very good numerics on treating that. Now, regarding the fast ejector, yes, they are part of the dynamical component, but they are different. And let me actually show this. If you can see the slide. So this is showing you a time integrated version of the mass ejection in terms of density and in terms of composition. And now you see that the main difference in the mass ejector for the fast ejector is simply that you have a secondary arm. So they're basically ejected in opposite directions. Just if you look back here, those fast ejector really move opposite from the main tidal tail that you would get in neutron star black hole and also neutron star because the tail is effectively the same. So you can basically just decide them based on the geometry where they fall. And then what we can do is we can track the composition also, and you can see that the fast ejector, just if you look at the colors, typically the ejector and neutron star black hole are almost pure neutron matter, but the fast ejector actually have significant proton fraction up to 0.2. So they're both different in terms of velocity and in terms of nuclear composition. And we can clearly distinguish that also from like in the direction which they are ejected. I hope that answers your question.
Oh yes, thank you so much. That's perfect. Thanks a lot.
Very good. Bruno, you have a next question?
Yes, I'm curious if you can say a bit more about the equation of state that you used, because, for example, I'm not very familiar with this one, the TNT.
Mm-hmm. So TNT YST is an equation of state based on the AVX18 argon potential. That's basically APR4, but finite temperature. They are very, very similar. And so you have initial stars that have a radius of about 11 kilometers and a maximum mass of about 2.2 solar masses.
Okay, and the other one is that contains hyperons, right? Or
the other one contains hyperons, exactly. I'm basically making this choice because I didn't want to have equation of state like DD2 with 2.4 solar masses maximum mass. So this is why I put the hyperonic version. But it doesn't matter because the interesting thing about those simulations, or in general about black hole neutron star or this particular mass range neutron star is since you never form a hypermassive neutron star really, you never probe the high density physics. So your density is only going to go down, and then those regimes, all of those equations of state have the same low density physics. So they're actually comparable in that sense. It's just the difference is how big the initial neutron star is that you put in, and that will determine the disk mass. That's the only difference those equations of state here really make. So the high density part is never probed in the simulation.
Okay, just one last question, just to be sure that very quick. Sorry if I can just to be sure that I understood correctly. The amplification you see in the magnetic field, is that due to MRI in the disk or something else?
Bruno, can you repeat the question? The connection just
yes. So the question, you say that by evolving a very long the simulation, you saw that there was some region where magnetic. So I just want to understand if that is due to MRI in the disk or was something else.
I think Elias is disappearing. Elias, are you with us?
Sorry, I'm back. Yes, I just missed out on the second part of the question. So you were wondering about the long-term behavior and how exactly the field builds up, I guess.
Yes, exactly. If that is magnetorotational instability or something else.
It is magnetorotational instability that is building up. The problem is you're starting this thing from a toroidal field. Actually, if you look at that paper, I did a very nice analysis of what the kind of topology of the field is, like how much toroidal field you have in terms of poloidal field at the time the disk forms, and you have 10 times more toroidal field, and the toroidal MRI just grows slower. So this is why this takes so long. It's just because you really have a toroidal field geometry. That makes the big difference compared to, let's say, when you look at people doing these supermassive black hole AGN simulations, where they put initial poloidal fields. Just the time scale gets longer.
Okay.
May I have a question?
Yes, please.
Mine is about the region of the funneling. So if you wait longer, then you have the magnetic field amplification. But what about the density? So I suppose that that region is clearing up bit by bit with the expansion of the material. So the density is decreasing, the density of the matter in that
exactly.
region. What is the value of the density that you have there?
So if you actually look, the right color, this violet thing, that's the inflow velocity. So the funnel is not clearing because material is flowing out, but rather it's flowing in. So that's what you would typically expect before the Blandford-Snijek sets in. It's kind of the black hole sucks in all the matter, and at some point you just build up enough magnetic pressure so to kind of keep the matter from falling in, and then you will eventually become almost force-free and launch the Blandford-Snijek. Now, if you look at the density values, we go to about 10 to the 7 grams per cubic centimeter in the funnel, or a little bit less. It just takes very, very long for the funnel to clear, because you always have, if you look at the lower half here, that's the density, you always have kind of shocks coming from the disk that start to pollute the funnel. So this just takes a long time to clear.
Okay, but still very dense.
It's still very dense, exactly. But that's because the accretion disk has densities of up to 10 to the 12 grams per cubic centimeters. So just have a reservoir, and it just, unless you build up enough magnetic pressure to keep the material from kind of being shocked in the funnel region, this will just continue on. But the nice thing is,
you can wait more.
You can wait more if you give me more compute time. So this simulation ran for like 3 months or so.
Yes, you can just wait more. Absolutely.
Exactly. I will do that next time. But
if you wait long enough, I think that you will have enough low density that with such a field, you can even induce a large electric field that will help you. That will can make the job even without Blandford-Snijek. You don't need that. You will not need that.
You mean because you will have something like Blandford pain, or how would you load the thing?
Oh, because in the case of a black hole with the magnetic field, you will induce a very large electric field, which is proportional to the magnetic field, and that magnetic field would be overcritical. That will create a lot of electron-positron pairs. That will push. They will push everything.
Yeah, exactly. Once you reach that stage, I'm fully with you. Once we get fully magnetically dominated, you would exactly go there. Yes, absolutely. It's just that if you look at the growth scale here, that's showing you the magnetic energy in the funnel. It just slows down after, like, it really amplifies over 50 milliseconds, and then it just grows slower. So it's still growing, but just at a lower rate.
Yeah, but the magnetic field, you have more than enough to do that. The problem is the density that you have to wait to be more clean. Very nice.
Okay. Any more questions or comments on that part, on that talk? If not, I was still looking for our last speaker and those primordial black holes, but no luck here. So let us just briefly summarize what we got during those 2 sessions. So it seems like we do have right now, we detect 3 sorts of mergers with LIGO and Virgo, and some of them with electromagnetic means as well. So double black holes, which are most frequent, LIGO Virgo mergers, are fully explained by number of models. Actually, we have a lot of models. Global clusters can explain them, binary evolution, AGNs. Actually, primordial black holes are being claimed as the origin of those LIGO Virgo black holes. So we have a lot of models that can explain many properties of those observed systems. When we switch down to black hole neutron stars, the thing seems to be also kind of simple, although a bit pessimistic in terms of electromagnetic counterparts. Like we do not expect a lot of mass ejections, so we will not expect many GRBs or kilonovae associated with black hole neutron star mergers. However, we do seem to understand and predict the right merger rates, at least from binary evolution, not from global clusters, as we heard today. But binary evolution can predict and provide the right rates and properties. For neutron stars, it seems like we are in a deadlock. We don't really know where they're coming from, at least given that one observation that could be like Alexandra was saying, could be still a statistical fluke, okay? So we do have still a lot of things to do and progress, and hopefully with, future observations of GRBs, high energy, observations, X-rays and electromagnetic observations, infrared and, optical kilonovae will be able to sort some of those issues out and actually pinpoint whether those mergers and detections are exactly what we think they are. Jorge, would you like to add something to that?
Yes, I would like just to add and to thank the speakers for the very honest talks, because I really see very honest talks here. In which were not uncritical and which were
hello.
But oh, here is
Florian. Sorry.
Yeah,
I had tremendous connection problems, but now it seems everything is over and working. So wonderful, absolutely fantastic. So yes, so
Florian, wait a second. Jorge was just making a summary. Let him finish that, and then we'll have you.
Sorry. Sorry.
No, that's fine. Let's Jorge finish.
I was just thanking the speakers for the very honest talks, because we're really pinpointing where there are critical problems with these issues. So we're not the typical, everything okay, we are observing these extremely nice things and we can explain everything. And it was actually the opposite. I mean, we were really saying we can't explain this. We have troubles here. This is what this is the way science can progress, and this is the real way we can go forward. And so I really thank you all for the spirit that you have had this session. And so thank you all for this. And so without taking more time, I will give a word to Florian.
Okay. Yeah, let's have this last talk as a final prize. I mean, a final prize of the session. Please go ahead. We'll 20 minutes.
Perfect. Okay. Thank you very much. So let me just share my screen. So let's see. So can you see this?
Yes, we can see that, and we can hear you.
Excellent. Wonderful. All right. So let's move this to here. So again, apologies for this is a little technical problem, but the black holes are now, closing this session. So I'm providing this horizon here. So anyway, so this talk will be about primordial black holes in general, and particularly about their formation properties, and also, how they could possibly be detected in terms of their signatures. And of course, it would be in terms of gravitational waves. Now, let's see. Yes. So, but first of all, let's start simple and let's start basic. So first of all, what are primordial black holes? Primordial black holes are black holes formed in the early universe. And depending on whom you ask, that time scale varies. So mostly it's before Big Bang nucleosynthesis, but really there's some models that produce them up to the meta-radiation equality. But usually they're produced in radiation domination. Actually, the very first paper was by Novikov and Zeldovich in the late 1960s. Not so much research, it was a quite negative conclusion, and not so much went on from there. So, but really, most work started when my dear collaborator, Bernard Carr, and together with his then PhD advisor, Stephen Hawking, who sadly passed away a few years ago, started working on this in the 1970s. And from then, I think Bernard wrote, I think, 120 papers on this subject. So it's been around for, say, 50 years or so. And I think now we are at a really crucial point in time where probably soon we will have, well, I would like to see evidence, but also first really strong constraints. And we'll talk about constraints very soon. But before I talk constraints, I'd like to say a few words about their formation. I mean, in astrophysics, we know there are black holes in the centers of almost any galaxy we find, and that goes up to masses of, I think, 10 to the 10 solar masses. And the lowest we could conceivably thinking of getting is whereby stellar collapse is around a solar mass. But I think a solar mass already a little bit challenging to make, to produce by this normal stellar collapse. But if you have heard about primordial black holes before, or some talks, I'm sure although in this conference, they can exist at much, much lower masses. I mean, orders of magnitude below. So, and let's think about how to establish this. So basically, if you have a look at a black hole occupies a volume and has a mass. So I can describe a density. So the density, as you see, decreases as the mass increases, or vice versa. So this tells us that actually for smaller black holes, we need sort of higher density environments. And this is precisely how people thought about formation of primordial black holes in the first place. So if you look at the average density of the cosmos, average density in Hubble patch, that decreases also, increases as time decreases, let's phrase it like this. And at some point you even surpass the density, which the would-be density, which you found in a solar mass black hole. This is precisely how people thought about formation of black holes. You have these quite high density environments. So the Hubble patch in the universe is basically of black hole density, if you like. And you need some perturbation, but you don't need so much. I will tell you how much in a moment, to sort of that re-enters the horizon and then makes what is in a certain horizon patch collapse. And when you do so, basically what you see is that the masses of the black holes and the times, they are sort of in an interesting range. So around the QCD phase transition, I like these handy things to remember, are basically solar mass black holes, which you would produce. Then there's another interesting mass scale, which is 10 to the 15 grams, which is those that if you believe that all evaporate down to the, by Hawking radiation, they would evaporate in the present epoch, and they have been produced rather early. So it's in 10 to minus 23 seconds after the Big Bang. So it's rather early sort of production. And as you can tell, imagine you would get probably the strongest constraints from these black holes. Now, let me see here. Yeah, and also I like that's what my collaborator Bernard Carr mentioned. So it's only about primordial black holes, only about because Stephen Hawking was thinking about black hole evaporation of small black holes, like these that could only be of primordial origin because they're so small, that he was led to his famous discovery of Hawking radiation. So, and like Bernard Carr always says, they are important even if never observed. And this is a sort of philosophical and interesting thought to have. So even if you don't observe them, they have had a tremendous impact in theoretical cosmology. Because a solar mass black hole basically lives, according to Hawking radiation, basically forever. It lives many orders of magnitude longer than the age of the universe. So this is basically what you would not, where it's hopeless to see any Hawking radiation. I don't know whether we will ever see, but that would live for a very long time. And these small black holes could actually evaporate within the Hubble time. Now, about formation of these objects, you can have hour-long talks about this, but let me just the main mechanism, summarize briefly the main mechanism, or list the main mechanism more precisely. So you can have cosmic string loops may intersect, and you may get a large enough energy density, similar to if you have first order phase transitions, you have a nucleation of bubbles all over the place. They may collide, or they collide, and then under certain circumstances, you can still get a large enough energy density in a certain region, which leads to the collapse of that region, and you form a black hole. Basically, in almost all phase transitions, and this is here, I have time to talk about this scenario where you have basically sort of the cosmic history with phase transition like the QCD phase transition, and you would get sort of during the phase transition reduction of pressure, and reduction of pressure helps sort of that over-densities collapse more easily because pressure works against this collapse. Then, and there's an interesting scenario, and I just advertised some work I'm doing with Geert Warling and a PhD student, Meko Santadeci, that is actually by quarks that are pushed by inflation apart, and then once they re-enter the horizon, can produce a black hole. So it's also something ongoing work. We're currently finalizing this project. But basically, most of the literature is discussing sort of density perturbations that are quite large and produced during inflation. And when you do so they are produced in the inflationary epoch, re-enter during, say, radiation domination, and then if they're above a certain overdensity, they collapse. And actually, when you assume a perfect fluid like P equal W rho, and it turns out that the overdensity, so delta is delta rho over rho, must be roughly bigger than the equation of state parameter, which would be a third for radiation. It's just a back of the envelope calculation, comparing the scale of the overdensity to the Jeans length, was done by Bernard Carr during his PhD time. And so that's, of course, so you have tremendous amounts of simulations that have been done, and complicated simulations, which arrive at a bit different value, but not too much different. So I want you to remember that the threshold for primordial black hole formation strongly depends on the equation of state. And I can tell you that the threshold is something the abundance depends exponentially on. So you're exponentially sensitive to the threshold, hence the equation of state parameter. That is why actually the dips in the equation of state during the QCD phase transition have such a large impact, which can boost the formation of primordial black holes by orders of magnitude. So how did it go? Here's a picture of the the scale of the scales in the universe, and this is a Hubble scale, how it evolves with time. And of course, it's basically constant during inflation. Then you have a radiation period, matter, and then something that looks like lambda. The physical scale leaves the horizon at some point and re-enters at another point. And once there's an overdensity associated with it that is above the collapse threshold, you would produce a black hole. Now, important to remember, those scales that leave earlier will re-enter later. So you have this inverse connection with time. So larger black holes probe earlier epochs, because you can also see them as probing the sort of inflationary potential, if you like. Now, where are these scales? So here I have the primordial power spectrum. And actually, if you look at the CMB, you basically probe, say, the last 9 E-folds or so. But where are primordial black hole scales? So basically, and this is actually, I'm telling you that, you don't need to mess around with your CMB scales, but actually the scales which are relevant in here are much, much below the CMB scales. So you have way smaller scales, and that's why you can produce, say, through a feature in the power spectrum leading to a peak of the power spectrum, say, reaching values of roughly 1%. And then you could get the production of primordial black holes. But when you have this scale and power spectrum again later, you can produce all your CMB fluctuations which you know and love. Now, and this is again something to remember. Primordial black hole scales, PBH always, if I haven't made it clear, stands for primordial black holes. So these scales for these objects are well below, I should have underlined, below CMB scales. Now, here's a constraint diagram, a bit older one, but the nice thing with this one is it's from the time of formation and stretches from here is a Planck mass, here's grams, so the mass of the primordial black holes in grams. So this is 10 to minus 5 grams, goes all over the way to 10 to the 50 grams, with 55 orders of magnitude in length. And here I have basically the fraction of collapsed horizon patches here. And everything above these lines is supposed to be constraints. So this is a measure for omega PBH. So it's basically the density fraction of primordial black holes. And you see it's really tiny. And here, see another thing. Here's basically the 10 to the 15 grams. The strongest constraints come from those mass ranges where primordial blacks would evaporate today. And if they evaporate today, they would shed a lot of gamma rays in all over the place, and you don't measure these. And from not measuring these, you can constrain the abundance very significantly. Another thing is here in this, at this time the diagram was drawn, in this range, there was basically no constraint. And if there's no constraint in here, you never see very small numbers. And of course, the reason being that the environment, so you produce them in radiation domination, which scales like scale factor to the power -4, and they are matter, so they dilute as a volume. So basically, the fraction of them, so omega PBH, increases like the scale factor. So, and that's why you have tiny fractions. For I think 10 to the 20 grams, it's basically 1 in 10 to the 15 horizon patches that must undergo a collapse. So it's almost, and this is to produce 100% of dark matter. So of course, if you produce less, the fraction will be even less. Okay. Here's a more recent constraint diagram from a paper of Bernard and myself from review and annual reviews. You have the primordial black hole dark matter fraction on this axis, and here you have the mass scale. There are a number of constraints which you have in here, and it's, again, you can give an hour-long talk, so details shall not matter. So I'm telling you that most of these landscape is basically significantly constrained, say by microlensing. This blue stands for microlensing. This is a Hawking radiation constraint, the red one. Then you get some accretion constraints, for instance, and there is large-scale scattering constraints, some CMB constraints even. So it's quite strongly constrained. But you do have some window where actually even for monochromatic mass functions, and this is only for monochromatic mass functions, you could have 100% of dark matter. So you could have 100% of dark matter and primordial black holes basically in this sort of 10 to the 20 gram-ish range, plus minus a few orders of magnitude. You can have some amount of here, some few percent, probably few percent around here, maybe even more, depending on how seriously you take these constraints. And sort of each constraint comes with assumption, and these assumptions, for instance, often disregard certain effects or certain possibilities. For instance, many lensing constraints are derived without taking clustering into account. So it makes a big difference, of course, observing a small patch of the sky if you have a homogeneous distribution or if they are very clustered in, say, 10,000s of objects. So, and if you include clustering, the constraints usually for lensing will get weakened. Now, another point to remember for these constraints is that basically they are redshift dependent. So it looks like always you get this presented like this, but actually really this is, no, each of these constraints comes from a certain redshift range. And you see, it's basically what you get is a projection. A thing to remember here, you have a plethora of constraints from really many different physical processes depending on the mass range, like if they evaporate, if they do microlensing, if they accrete, or if they even destroy neutron stars. Because they could sink in the centers of neutron stars and then destroy them. And so there's a ton of constraints, but also each of these constraints is subject, first of all, to a certain redshift range, and also is subject to many assumptions. So it's astrophysical assumptions. And if you look at constraints and if people tell you this mass window is closed, think critically and ask critically, what are the constraints assumptions here? Now we come to what I really want to talk about also in some remaining minutes, and then give you a model to talk about more how these signatures could be generated. So primordial black holes, of course, since they are black holes, can emit gravitational waves in various instances and times. Now, first of all, and this is sort of the first thing you encounter, is gravitational waves from their formation. So you have a large overdensity that collapses. And even so, at first order perturbations, you don't get any constraints. So it's because it's a small scalar collapse. You will, at second order or higher orders in perturbation theory, you generate tensor perturbations that manifest themselves as gravitational waves. And these gravitational waves may be observed. It's depending quite heavily on how many non-Gaussianities you have, and and other factors as well. But this is basically the first thing that generates gravitational waves. The second thing is, so please.
3 minutes, okay? 3 minutes.
A few minutes, yes, that's perfect, yeah. Thank you. So, and now the second thing is that the second source of gravitational waves is if you form binaries, but binaries at early times, that probably, you know, if primordial black holes constitute the entirety of the dark matter or a significant fraction of that, you will have, you know, binary formation all over the place. If you have binary formation all over the place, you have sort of some stochastic gravitational wave background, and this may be observed with certain, depending on, you know, what you assume for the mergers and the environments and clustering, but they may be observed with different with gravitational wave observatories. The next thing is that, well, we could look at individual mergers, so such as we observed with LIGO, Virgo, and our Cactra comes into the game, so and probably what we will observe with other observatories as well. And individual mergers, so primordial black holes can easily be produced at order 10 solar masses. So in principle, what we have observed could be of primordial in nature. And then the next question is how to discriminate primordial black holes from astrophysical black holes. Because if they're in the same mass, and black hole at the classical level at least doesn't have exactly many features, the charge is basically unimportant. So you have the mass, which is degenerate, leaves the spin. So the spin, actually, what is interesting when you look at the formation of primordial black holes by this collapse of horizon size fluctuations of inflationary origin, and they are produced in the radiation-dominated era, you would, you know, find that basically most of these black holes have spin which is close to either 0 or close to 0. So, and let's have a look at what LIGO observed. So this is basically here a diagram showing a number of recent gravitational wave observations from binary mergers, and then this is the sort of the effective spin parameter, which is defined in here, which is basically a weighted projection. So mass weighted projection. So the SJs are the spins of the individual black holes weighted by the mass projected on the total angular momentum. And you see, it's not a proof, but at least it shows consistency with the hypothesis that these black hole mergers may be of primordial origin. So basically all of those have a very low spin, effective spin parameter. Of course, as a disclaimer, this spin parameter can be even 0 for very large individual spins, but that would require some sort of particular arrangement of an alignment, but which you cannot, there's no reason to believe this. So basically you see most of them don't spin very much, and this is what you would expect from primordial black holes. There's another source yet, and I must mention this. So it's by gravitational Bremsstrahlung. So you have even more than mergers. So if you have primordial black holes as a sort of dominant or significant contribution of dark matter, you have even many more encounters, close encounters. And these encounters would sort of radiate sort of gravitational waves. It's similar to Bremsstrahlung, and this you could potentially measure also in the future with LISA, for instance. So there's a number of there's 4 different sources of gravitational waves, and so spin being one of the main discriminator. So like I said, this is. But also what I pointed out that maybe in the future, not maybe, but in the future, we will see observations, we will have observations that either limit very much the primordial black hole abundance, like really undoubtedly, or in the mass range the detectors are looking at, or we would find these black hole mergers, and you know, if more to come, like LIGO is in Virgo Kegra, there's hundreds of primordial black, I hope primordial, but there's hundreds of black hole mergers to be detected. So we can talk about the spin distributions, compare them. Of course, the smoking gun here would be observing black holes below a solar mass, because these are even significantly below a solar mass. These would basically not be able to be produced from stellar collapse, which are usually significantly above 1 solar mass. So that would be a smoking gun.
Okay, we need to wrap it up, Florian. We need to wrap it up.
Yeah. So I'm basically done. So well, let's. So this is what I want you to remember here. So well, there's this model. I can probably in the questions or in private communication later tell you about that the phase transitions basically sort of lead to a natural formation scenario which produces even the seeds for supermassive black holes, the LIGO black holes, and in the planetary mass range, and yet giving all over 100% of the dark matter for primordial black holes. This is a model that I developed with Bernard Carr, Juan Garcia Belido, and Sebastian Klass, and this is called Cosmic Conundra. If you want to search it, you can also email me, because that is a scenario that can account for sort of all of these observed black holes. And so it comes from the thermal history of the universe, but and also made a prediction of LIGO black holes. But let me finish with this slide, which also my dear collaborator Bernard Carr likes to show, shows the link of primordial black holes, or as let me phrase it differently, shows primordial black holes as a link between micro and macro physics. So connecting, if they exist and are produced by these inflationary fluctuations, the scales from very early epochs to the very large, even up to, you know, black holes, which we call slabs, which are above these, what you usually measure in the centers of galaxies. So with this slide, I end my talk, and so thank you for your attention. Sorry for again for being late and having taken you on a rush through these aspects of primordial black hole.
Okay. Thank you very much. We will gonna get cut off by organizers if we don't stop here. So I want to give people a chance to ask some questions. Okay.
Good. Please.
Yes. Okay. So very good. You know, introduction to primordial black holes. Good results. I have some disagreements, but I let first other people ask questions or comment if there are any. Please go ahead. The paper is open for questions or comments. Or maybe if people are deciding, let me have my comment then. So
please, I mean, I love if you have disagreement. I love to you know people disagreeing with me.
I agree. So for me, the most important issue here is how we tell them apart from primordial black holes from astrophysical black holes, like you were emphasizing that in your last few slides. So I fully agree with you that observing black holes or actually compact objects below 1 solar mass, like 0.5 or even below, because 1 solar mass, it could be neutron stars. You will not know whether it's a neutron star or a black hole, but 0.5, you will know it needs to be a primordial black hole. So that's a smoking gun. However, black hole spins are no-go because stars are producing low spinning black holes. End of the story. I mean, entire evolutionary community right now is producing low spinning black holes. So you have a total degeneracy with primordial black holes. That's unfortunate, but it is what it is. So this
Oh
is
yeah,
no
no,
doubt.
I see. Yeah, actually, I mean, let me phrase it differently. So if basically all the LIGO spins were, you know, very large, then I would say it's not primordial black hole. Let me phrase it more like this. Yes, I agree. There's degeneracy, but it's sort of, it shows that it's not inconsistent on this level. I mean, I fully agree that. Yeah, no, I agree. I would not claim that's true. I would not claim that the spin is a clear discriminator between primordial and astrophysical black hole. I fully agree with you here.
Thanks for clarification, because it didn't sound that way. It sounded like you showing that as a smoking gun, but it's okay.
No,
So
okay. Then if that came across, I guess, I'm sorry. I thought I said, but probably I said it wrong. It probably sometimes things in my head. So you know, at least it's sort of not inconsistent. It's sort of I don't know whether I can call it indication, but at least what I think we can agree on that this is
consistent.
It's consistent. It's not inconsistent. So it's consistent. But of course, we would love to see sort of some subsolar and really significantly subsolar compact objects like black holes, like really compact objects. Then we would have the clearest signature of.
There is one more smoking gun, actually, which you didn't mention. If we do, stars are not supposed to produce black holes beyond redshift 30 or 40.
Yeah.
So if we have Einstein telescope or cosmic explorer that will probe entire universe, and we see merger rate increasing with redshift towards large redshifts, it doesn't have to be to redshift 40. If we do actually see black hole merger rates showing up beyond redshift 10, I think that would be your primordial black holes as well.
Yeah, absolutely.
And so, for now, you're still consistent with LIGO, because LIGO is showing increase of black hole merger rate with redshift, but it's so far also consistent with stars, because we do produce merger redshift rising with redshift up to redshift 2. So unfortunately, it's inconclusive. It's consistent with both, but inconclusive. But sooner or later, we will know. So this is very exciting.
That is true. That is true. I mean, to give one more. Put one more ball into the game. I mean, I think my collaborator Katie Fries, who is sort of advertising dark stars, she would probably say that, well, at the remnant of dark stars, you could still get black holes which are not primordial at origin. So there's and also there's probably other exotics, and I've also worked on something where you produce other compact objects. Or if you ask, I remember a talk by Glenn Starkman at some point. He talked about macroscopic dark matter. You can have an object of nuclear density, but I think this is probably more exotic. I think from the sort of very high redshift or very low mass object, probably the primordial black holes are, I would say, the most feasible ones which you may think about. It's also another point is that if you think of them as sort of dark matter candidates, it is in a way a conservative dark matter candidate, in the sense that when you produce them via inflation, you do not need another particle. So you have the mechanism of producing a black hole is the same. A primordial black hole and the normal black hole is the same. So if you have a feature in the inflationary potential, then you don't need another particle or new interaction. So basically you would produce within sort of, okay, it's not really the standard model because it has inflation, but once you have inflation, well, in principle, you don't need much else to produce this object. So in this sense, it's sort of a conservative candidate.
Okay. Thanks for comment. If we don't have any other comments or questions, Jorge, I think we should probably end the sessions because we're going to get cut off anyway.
Yes, and we have to rush to the plenary because they are already starting.
Yes, plenary sessions are starting. So thank you to all the speakers for giving talks. Thank you for all the comments and questions. And we
look forward for the proceedings, please.
Yes.
Please write your contributions for the proceedings. It will appear the information on the web page.
Yes.
That will be electronic, so there will be not that usual cut of 6 pages or so. So you can write really nice contribution this time.
Mm-hmm.
Okay, thank you very much, and see you on plenary sessions if you're interested in those. Thank you. Goodbye, everyone.
See you guys. Bye bye.
Thank you.
Thank
Bye.
you.
Thank you. Bye.